Right now, as you read or listen to these words, your body is conducting a symphony of sensory interpretation. Light waves are striking your retinas, converted instantly into neural signals your brain decodes as letters and meaning. Sound waves are vibrating delicate bones in your ears, perhaps carrying these very words to your consciousness. You're likely aware, if you pause to notice, of the pressure of a chair beneath you, the texture of fabric against your skin, the temperature of the air. You might smell something distant: coffee brewing, rain approaching, the faint scent of soap or fabric softener, without having consciously decided to notice it. These sensations don't just happen to you, they are you, or at least they're how you construct what you experience as reality. Your five senses are not merely windows to the world, passive receivers of information waiting out there to be collected. They are the architects of your conscious experience, the translators of physics into feeling, chemistry into meaning, the builders of the only world you'll ever actually know. Before we explore each sense individually, it helps to understand what all sensory systems have in common. Beneath their obvious differences, vision, hearing, touch, taste, and smell all operate according to the same fundamental principles. They detect specific forms of energy or chemical information from the environment, convert that information into the language the nervous system understands, transmit it to the brain, and there, through processes we still don't fully comprehend, transform it into conscious experience. This process unfolds in four essential stages. First comes stimulus detection. Something in the environment, a photon of light, a molecule of vanilla, a vibration in the air, makes contact with a specialized receptor cell. These receptor cells are biological specialists, each type exquisitely tuned to respond to one particular form of stimulation and largely indifferent to others. The photoreceptors in your retina respond to electromagnetic radiation in a narrow band of wavelengths, but ignore sound waves entirely. The hair cells in your inner ear deflect in response to mechanical movement, but remain unmoved by light. This specialization makes sense. A sensory system that responded to everything would be overwhelmed, unable to extract meaningful information from the chaos. Second comes transduction. This is where the magic happens, if you're inclined toward metaphor, or where biophysics does its work, if you prefer precision. Transduction is the conversion of environmental energy into electrical and chemical signals that neurons can process. When light strikes a photoreceptor, it triggers a cascade of molecular events that ultimately changes the cell's electrical charge. When a tastant molecule binds to a receptor on a taste cell, it opens ion channels, allowing charged particles to flow across the membrane. The specifics vary by sensory system, but the outcome is always the same: a graded electrical change called a receptor potential. If this potential is strong enough, it triggers action potentials, the all or none electrical spikes that neurons use to communicate over distance. Third is transmission. Sensory information must travel from the periphery, your fingertips, your tongue, your retina, to the central nervous system where it can be interpreted and acted upon. This journey occurs along sensory neurons, specialized cells with long projections called axons that can extend remarkable distances. Some sensory neurons stretch from your toes to your spinal cord, over a meter in length in a tall person. These neurons don't simply pass information along passively. They encode it, translating the intensity, duration, and quality of stimulation into patterns of electrical activity. A gentle touch might produce a few widely spaced action potentials. A sharp pain generates a rapid, sustained barrage. Finally comes perception, the transformation of neural signals into conscious experience. This is where sensation becomes perception, where physics becomes psychology. Perception happens in the brain, primarily in specialized regions of the cerebral cortex dedicated to processing particular types of sensory information. The visual cortex occupies much of the back of your brain. The auditory cortex sits on the sides. The somatosensory cortex, which handles touch and related sensations, runs in a strip from roughly ear to ear across the top of your head. But perception isn't simply a matter of signals arriving at these cortical regions and experience emerging automatically. The brain actively constructs perceptual experience, filling in gaps, making predictions, integrating current sensory input with past experience and expectations. What you perceive is not a direct readout of what's out there in the world, but a model, a best guess, constructed by your brain based on available evidence. This raises an important point that will recur throughout our exploration of the senses. Perception is inherently subjective. Two people can receive identical sensory input and yet perceive different things. The classic example involves color. The wavelengths of light reflecting from an object are objective, measurable, but the experience of color, what it's like to see red or blue or green, is subjective, private, inaccessible to outside measurement. We assume that when we both look at a red apple and call it red, we're having similar experiences. But we can't be certain. You might experience what I would call green if I could somehow access your consciousness, and we'd both still learn to use the word red for the same wavelengths. More dramatically, people differ in their sensory capabilities in ways that create genuinely different perceptual worlds. Some people are colorblind, unable to distinguish certain wavelengths, others easily differentiate. Some are supertasters, possessing more taste buds than average and experiencing flavors more intensely. Some have anosmia for specific odorants, unable to smell compounds others detect readily. Some experience synesthesia, where stimulation of one sensory modality produces perception in another, hearing colors or tasting shapes. The sensory world you inhabit is not quite the same as anyone else's. Sensory systems also exhibit thresholds, limits on what they can detect. The absolute threshold is the minimum stimulus intensity required for detection. For vision, under ideal conditions, this is remarkably low. A single photon can trigger a response in a rod photoreceptor, though you need several to reach conscious awareness. For hearing, you can detect a sound that moves your eardrum less than the diameter of a hydrogen atom. These thresholds aren't fixed. They vary based on adaptation, attention, expectation, and the current state of the sensory system. The difference threshold, also called the just noticeable difference, is the minimum change in stimulus intensity required to detect that something has changed. This follows Weber's law, which states that the change needed is proportional to the starting intensity. If you're holding a 5-pound weight, you might need to add half a pound to notice the difference. If you're holding 50 pounds, you'd need to add 5 pounds to notice. The ratio stays constant even as absolute values change. Sensory adaptation is another universal property. When exposed to constant stimulation, sensory systems become less responsive over time. This makes sense from an information perspective. Constant, unchanging input conveys little useful information. What matters is change, something new appearing, a stimulus intensifying, a threat emerging. Adaptation allows sensory systems to remain sensitive to change while avoiding saturation from constant background stimulation. This is why you stop noticing the feeling of your clothes after you've been wearing them for a few minutes, why you cease to smell your own home's particular scent, why constant sounds fade into the background. The stimulation hasn't stopped. Your sensory system has simply stopped paying attention to it. Finally, and perhaps most importantly, sensory systems don't operate in isolation. They constantly interact, integrating information across modalities to create unified perceptual experience. When you eat an orange, you're not experiencing taste, smell, texture, color, and sound as separate inputs. You're experiencing orange, a unified multisensory perception. When you watch someone speak, your brain automatically integrates the auditory information, the sounds they're making, with the visual information, the movements of their lips and face. This integration is so automatic, so fundamental, that it can create perceptual illusions when the inputs conflict. The brain regions responsible for integrating multisensory information include association areas of the cortex, regions that receive input from multiple sensory systems and whose neurons respond to combinations of stimuli. The posterior parietal cortex, for instance, integrates visual, auditory, and somatosensory information to create spatial awareness, your sense of where things are around you and where your body is in relation to them. Without this integration, you'd experience the world as a disconnected collection of sensations rather than a coherent environment you can navigate and interact with. This architecture, detection, transduction, transmission, and perception, with its thresholds, adaptation, and integration, forms the foundation upon which all sensory experience is built. Each sense elaborates on this basic plan in its own way, with specialized receptor cells, unique transduction mechanisms, and dedicated neural pathways. But beneath the details, the principles remain constant. Understanding this common architecture allows us to appreciate both what makes each sense unique and what they all share. The remarkable ability to convert the physical and chemical properties of the world into the rich, meaningful, conscious experience of being alive and aware. With this framework established, we can now turn our attention to the specific senses themselves, beginning with the one that dominates human experience more than any other. Vision processes more information, occupies more brain tissue, and shapes more of human behavior than all the other senses combined. It's where we'll begin our detailed exploration of how the five senses connect you to the world. Of all the senses, vision dominates human experience to an extent that can be difficult to fully appreciate until you stop to consider it. Roughly 1/3 of your cerebral cortex is devoted in some way to processing visual information. More brain tissue, more neurons, more computational resources are dedicated to sight than to any other sense. When people imagine losing a sense, vision is typically the one they dread most. This isn't mere cultural bias. It reflects the extraordinary importance vision has in how humans navigate, understand, and interact with the world. The human eye is an optical instrument of considerable sophistication, a living camera that captures light and converts it into neural signals. Each eye is roughly spherical, about an inch in diameter, and sits protected within a bony socket in the skull called the orbit. Only about 1/6 of the eye's surface is visible from the outside. The rest remains hidden, cushioned by fat, and served by 6 muscles that allow it to move and aim with remarkable precision and speed. The eye is constructed in layers, 3 concentric coats, each serving distinct functions. The outermost layer is the sclera, the white of the eye, a tough fibrous tissue that maintains the eye's shape and provides attachment points for the muscles that move it. At the front of the eye, the sclera becomes transparent, transforming into the cornea. This clear, curved window performs much of the eye's light bending work. In fact, the cornea provides about 2/3 of the eye's total refractive power, more than the lens behind it. Its curvature and the difference in refractive index between air and the corneal tissue bend incoming light rays, beginning the process of focusing an image onto the back of the eye. The middle layer, the choroid, is a thin membrane rich with blood vessels. It supplies oxygen and nutrients to the outer layers of the retina and contains pigmented cells that absorb stray light, preventing it from scattering within the eye and degrading image quality. Think of it as the black paint inside a camera body, there to prevent internal reflections. At the front of the eye, the choroid transforms into the ciliary body and the iris. The ciliary body contains the ciliary muscle, which controls the shape of the lens and produces the aqueous humor, the clear fluid that fills the space between the cornea and the lens. The iris is the colored part of the eye, the structure that makes your eyes blue or brown or green, but color is merely a side effect of the iris's actual function, controlling how much light enters the eye. The iris operates as an adjustable aperture, similar to the diaphragm in a camera lens. At its center is an opening called the pupil, which isn't a structure itself, but simply the hole in the middle of the iris. The iris contains two sets of smooth muscle fibers. Circular muscles, when contracted, make the pupil smaller, a process called miosis. Radial muscles, when contracted, make the pupil larger, mydriasis. These adjustments happen automatically and continuously in response to ambient light levels. In bright conditions, the pupil constricts to perhaps 2 millimeters in diameter, protecting the sensitive retina from excessive light. In darkness, it can dilate to 8 millimeters or more, gathering as much light as possible. This gives the eye a functional range of about 16:1 in light gathering ability, though adaptation of the photoreceptors themselves extends the total dynamic range to perhaps 1,000,000:1. Behind the iris sits the lens, a remarkable structure composed almost entirely of specialized proteins called crystallins, arranged in precise layers. Unlike most body tissues, the lens contains no blood vessels. It receives nourishment from the surrounding aqueous and vitreous humors by diffusion. The lens is suspended by fine ligaments called zonules, which connect it to the ciliary body. When the ciliary muscle relaxes, the zonules pull taut, stretching the lens into a flatter shape. When the ciliary muscle contracts, the zonules slacken, and the lens, being elastic, springs into a more rounded form. This change in shape changes the lens's refractive power, allowing the eye to focus on objects at different distances, a process called accommodation. When you look at something distant, the ciliary muscle is relaxed, the lens is flat, and light from distant objects focuses precisely on the retina. When you look at something close, say a book or your phone, the ciliary muscle contracts, the lens rounds up, increasing its refractive power to bend the light rays more sharply, keeping the image focused. This ability to accommodate decreases with age as the lens gradually loses its elasticity, leading to presbyopia, the condition that sends people reaching for reading glasses, typically in their 40s. Behind the lens, filling most of the eye's interior, is the vitreous humor, a clear gel that gives the eye its shape and helps maintain the retina's position against the back wall of the eye. Unlike the aqueous humor, which is continuously produced and drained, The vitreous humor is formed during development and isn't replaced. Sometimes fibers within the vitreous clump together, casting shadows on the retina that you perceive as floaters, those odd little shapes that drift across your visual field, especially noticeable against bright backgrounds. Finally, we reach the innermost layer, the retina. This is where light energy becomes neural information. The retina is, in essence, a piece of brain tissue that migrated to the back of the eye during development. It's actually an outgrowth of the central nervous system, which explains why it contains neurons and why damage to it is generally permanent. Neurons in the retina, unlike many other cells in the body, don't regenerate. The retina is organized in layers, perhaps counterintuitively, with the photoreceptors, the light-sensitive cells, at the very back, farthest from the incoming light. Light must pass through several layers of neurons and support cells before reaching the photoreceptors. This seems like poor design until you consider that the photoreceptors have enormous metabolic demands, consuming oxygen and nutrients at prodigious rates. Placing them directly against the choroid with its rich blood supply makes sense from a supply line perspective, even if it means light has to pass through some neural tissue first. Fortunately, these overlying cells are largely transparent, and in most of the retina, they're thin enough not to degrade the image significantly. There are two types of photoreceptors, rods and cones. Rods, numbering about 120 million per eye, are exquisitely sensitive to light and operate well in dim conditions. They're responsible for night vision, scotopic vision, as it's technically called. However, rods don't discriminate wavelength, which is why everything looks gray in very low light. The old saying, "At night, all cats are gray," captures this nicely. Rods are distributed primarily in the peripheral retina, which explains why you can sometimes see a faint star by looking slightly to the side of it using your rod-rich periphery, but lose sight of it when you look directly at it. Cones, of which you have about 6 million per eye, are less sensitive than rods, but function in brighter light and provide both better spatial resolution and color vision. There are three types of cones, each containing a different photopigment that responds best to a particular range of wavelengths. Short wavelength cones, sometimes called S cones or blue cones, peak in sensitivity around 420 nanometers in the blue range. Medium wavelength cones, M cones or green cones, peak around 530 nanometers. Long wavelength cones, L cones or red cones, peak around 560 nanometers in the yellow-green range actually, though we label them red for convenience. Color vision emerges from comparing the relative activity of these three cone types. Different wavelengths stimulate the three types to different degrees, and the brain interprets these patterns as different colors. This trichromatic system has limitations. We can't see ultraviolet or infrared light, wavelengths outside the roughly 400 to 700 nanometer range visible spectrum. Some animals, bees for instance, can see ultraviolet light and perceive patterns on flowers invisible to us. Some snakes can detect infrared radiation using specialized pit organs, allowing them to see the heat signature of warm-blooded prey. Our visible spectrum is simply the slice of the electromagnetic spectrum that our particular photopigments happen to absorb. Cones are concentrated in the central retina, especially in a small region called the fovea, a pit about 1.5 millimeters in diameter, located at the center of a larger region called the macula. The fovea is the location of highest visual acuity. When you look directly at something, you're positioning its image on your fovea. Here, The overlying neural layers are pushed aside, allowing light to strike the cones directly without passing through other cells first. The cones in the fovea are tightly packed, thinner than elsewhere, and each cone has essentially a private line to the brain via its own bipolar and ganglion cells. This one-to-one connection preserves fine detail. In the peripheral retina, many photoreceptors converge onto single ganglion cells, which increases sensitivity, more inputs sum together, but decreases resolution. Fine spatial details are lost in the pooling. The other retinal neurons process information before it leaves the eye. Photoreceptors synapse onto bipolar cells, which in turn synapse onto ganglion cells. But this vertical flow is modulated by horizontal cells and amacrine cells, which mediate lateral interactions, allowing nearby regions of the retina to influence each other. This creates receptive fields with center surround organization. A ganglion cell might be excited by light in the center of its receptive field, but inhibited by light in the surrounding ring, or vice versa. This arrangement enhances sensitivity to edges and boundaries while becoming less responsive to uniform illumination, a useful adaptation since edges and contrasts contain more information than flat fields of even brightness. The axons of the ganglion cells bundle together and exit the eye as the optic nerve. At the point where the optic nerve exits, there are no photoreceptors, creating a blind spot in each eye. You're not normally aware of this blind spot because your brain fills in the missing information based on the surrounding context, and because the blind spots of the two eyes don't overlap, each eye covering for the other's gap. But you can demonstrate its existence easily enough with the right target and a little patience. The optic nerves from both eyes travel back to the brain, meeting at the optic chiasm, a location just in front of the pituitary gland, where the nasal fibers from each eye cross to the opposite side of the brain. Temporal fibers from the outer half of each retina remain on the same side. This partial crossing means that each half of the brain receives information from the opposite half of the visual field. The right visual cortex processes information from the left visual field, and vice versa. If you suffer damage to your right visual cortex, you lose vision in the left half of the visual field in both eyes. After the optic chiasm, the fibers travel as the optic tracks to a relay station in the thalamus called the lateral geniculate nucleus, or LGN. Here, the information is sorted and organized. The LGN has 6 layers, each receiving input from one eye, 3 layers per eye, with different layers processing information from different types of ganglion cells. From the LGN, neurons project to the primary visual cortex, also called V1 or striate cortex, located at the very back of the brain in the occipital lobe. V1 is where conscious visual perception begins. Neurons here respond to simple visual features, edges, oriented lines, motion in particular directions. The cortex is organized in columns, with nearby neurons responding to similar features. A column of neurons might all respond best to vertical edges, while the adjacent column prefers edges tilted 15 degrees to the right. This columnar organization repeats across V1, creating a computational architecture that extracts basic visual features from the incoming image. But V1 is just the beginning. Information flows from V1 to perhaps 36 additional visual areas, each specialized for processing particular aspects of vision. Some areas specialize in motion detection. Damage to area MT, for instance, can produce achinotopsia, an inability to perceive motion smoothly. Affected individuals see the world as a series of static snapshots rather than continuous movement. Other areas specialize in color, form, or spatial relationships. The ventral stream, flowing from V1 toward the temporal lobe, is sometimes called the what pathway because it's involved in object recognition and identification. The dorsal stream, flowing from V1 toward the parietal lobe, is the where or how pathway involved in spatial vision and visually guided action. This distributed processing means that vision is not constructed in one place. There's no single location where you watch a mental movie of the visual world. Instead, different aspects of the visual scene are analyzed in parallel by different specialized brain regions, and somehow, through mechanisms still not fully understood, these separate analyses are bound together into unified perceptual experience. This binding problem, how the brain integrates color processed in one region, motion in another, form in a third, into the coherent perception of a single moving colored object, remains one of the great puzzles of neuroscience. Vision also requires movement, specifically eye movement. Your eyes are never truly still. They make small, rapid movements called microsaccades, even when you try to fixate steadily, and they make larger saccadic jumps several times per second as you scan a scene, redirecting your fovea to objects of interest. These movements are essential. If an image is perfectly stabilized on the retina using special equipment, it fades from consciousness within seconds. The visual system needs change, needs motion, to maintain perception, depth perception, the ability to judge distances and see the world in 3 dimensions, emerges from multiple cues. Binocular cues depend on having 2 eyes. Because your eyes are separated by a few inches, they see slightly different views of the world. This binocular disparity is the basis of stereopsis, the vivid depth perception you experience when both eyes work together. The brain compares the images from the 2 eyes and uses the differences to compute distance. This is how 3D movies work. They present slightly different images to each eye, mimicking natural binocular disparity. But stereopsis isn't the only source of depth information. Monocular cues, available even with one eye closed, include relative size. Objects farther away appear smaller. Occlusion, near objects block the view of distant ones. Linear perspective, parallel lines appear to converge with distance. Texture gradients, fine details become less distinct with distance. And motion parallax, near objects appear to move faster than distant ones when you move your head. The brain integrates all available cues to construct depth perception, which is why people who lose sight in one eye can still navigate effectively after a period of adaptation. Vision is subject to numerous illusions that reveal how actively the brain constructs perception. The brain makes assumptions, uses shortcuts, predicts what should be there based on past experience. Usually, these strategies work well. Sometimes they produce systematic errors, illusions where what you perceive differs from physical reality. Some illusions exploit the center-surround organization of receptive fields, creating simultaneous contrast effects where the same gray patch appears lighter or darker depending on its surround. Some exploit motion processing, creating apparent motion in static images. Some exploit depth cues, creating impossible objects that your visual system gamely tries to interpret as 3-dimensional structures, even though they can't exist in physical space. These illusions aren't failures of the visual system. They're revealing its operating principles. showing how perception is constructed through inference and interpretation rather than simple readout of sensory data. The visual world you experience is a model, a controlled hallucination, as some neuroscientists provocatively put it, constructed by your brain based on sensory input, but not identical to that input. Common visual impairments reveal what can go wrong at different stages of the visual pathway. Refractive errors, myopia or nearsightedness, hyperopia or farsightedness, and astigmatism occur when the eye's optics don't focus light precisely on the retina. In myopia, the eyeball is too long or the cornea too curved, causing light from distant objects to focus in front of the retina. In hyperopia, the opposite problem produces focus behind the retina. Astigmatism results from uneven curvature of the cornea or lens, creating different focal points in different planes. All can be corrected with lenses that adjust the refraction to restore focus. Cataracts, clouding of the normally clear lens, become common with age. They develop gradually, progressively scattering light and reducing the amount that reaches the retina, causing vision to become dim and blurry. Fortunately, cataract surgery, replacing the clouded lens with an artificial one, is routine and highly successful. Glaucoma involves damage to the optic nerve, often associated with increased pressure within the eye. It typically affects peripheral vision first, gradually constricting the visual field. Without treatment, it can lead to complete blindness. Macular degeneration, particularly age-related macular degeneration, damages the central retina, affecting fine detailed vision while leaving peripheral vision intact. More dramatically, damage to the visual cortex can produce strange perceptual deficits. Lesions to one can produce blind spots in the visual field, scotomas, where the person cannot consciously see anything. Yet in some cases, patients with scotomas show blind sight, the ability to respond to visual stimuli in the blind region despite denying any conscious perception. This suggests that visual information can influence behavior even without reaching consciousness, mediated by pathways that bypass V1. Vision, then, is not simply a matter of opening your eyes and the world appearing. It's an active process of gathering information through precisely controlled eye movements, transducing light energy into neural signals through elegant photochemistry, transmitting those signals through multiple processing stages, and constructing in distributed brain networks a coherent, meaningful, three-dimensional perceptual representation of the environment. It's a process so complex that we've only begun to understand it, and so automatic that it feels effortless. When functioning properly, vision provides information so rich, so detailed, and so immediately useful that it dominates conscious experience and shapes how we think about knowledge itself. We speak of seeing the truth, of vision as understanding, of insight and enlightenment. Vision, for better and worse, is how most humans primarily relate to the world. But vision is not the only sense providing rich information about the environment at a distance. Sound, traveling through air as pressure waves, carries detailed information about events near and far, often from sources outside the visual field. Hearing complements vision, filling in what eyes cannot see, alerting us to dangers behind us, allowing communication through speech, enriching experience with music. It's to this temporal sense, hearing, that we turn our attention next. Sound is physics made audible, vibrations in air translated into conscious experience. Unlike light, which travels through the vacuum of space, sound requires a medium, molecules of air or water or solid material that can be compressed and rarefied in rhythmic waves. When something vibrates, a speaker cone, a guitar string, vocal cords, it pushes against adjacent air molecules, creating regions of slightly higher pressure. These molecules push against their neighbors, propagating the disturbance outward as a wave. Between the compressed regions are rarefactions, areas of slightly lower pressure. This pattern of compressions and rarefactions spreading through the air is what we call a sound wave. The ear's job is to detect these pressure variations, analyze them, and convert them into neural signals the brain can interpret. It's a remarkable feat of bioengineering, taking mechanical vibrations in air and transforming them into the subjective experience of hearing, the recognition of a voice, the beauty of music, the meaning of language, the warning of approaching danger. The ear divides into three anatomical regions: outer ear, middle ear, and inner ear. Each plays a distinct role in the journey from sound wave to perception. The outer ear consists of the pinna, the visible part, and the ear canal leading inward to the eardrum. The pinna, with its complex folds and ridges, is more than decorative. Its shape helps gather sound waves and provides cues for localizing sounds in the vertical plane, distinguishing whether a sound comes from above or below. The ear canal, roughly an inch long and lined with skin that produces protective earwax, acts as a resonant tube, amplifying frequencies in the range most important for speech, around 2000 to 4000 hertz. At the inner end of the ear canal sits the tympanic membrane, the eardrum, a thin cone-shaped membrane that vibrates in response to sound pressure waves. The eardrum is remarkably sensitive. A whisper causes it to move less than the diameter of a hydrogen atom. A loud sound can produce movements thousands of times larger. This extraordinary dynamic range is preserved throughout the auditory system. The middle ear is an air-filled cavity behind the eardrum, containing the three smallest bones in the human body. These ossicles, the malleus or hammer, incus or anvil, and stapes or stirrup, form a mechanical chain that transmits vibrations from the eardrum to the inner ear. The malleus attaches directly to the eardrum, so when the eardrum moves, the malleus moves with it. The malleus connects to the incus, which in turn connects to the stapes. The stapes presses against a membrane-covered opening called the oval window, which marks the entrance to the inner ear. This chain of bones does more than simply relay vibrations. It provides mechanical amplification through leverage. The ossicles act as a lever system, and the area of the eardrum is much larger than the area of the oval window, concentrating force into a smaller area and thus increasing pressure. Together, these factors provide about 20 to 30 decibels of amplification, crucial for overcoming the impedance mismatch between air and the fluid-filled inner ear. Without this amplification, much of the sound energy would simply reflect off the inner ear, unable to enter. The middle ear also contains two small muscles. The tensor tympani attaches to the malleus, and the stapedius attaches to the stapes. These muscles can contract in response to loud sounds, stiffening the ossicular chain and reducing the amount of energy transmitted to the inner ear. This acoustic reflex provides some protection against damage from sustained loud noise, though it's too slow to protect against sudden loud sounds like gunshots. Interestingly, the stapedius contracts just before you speak, dampening the sound of your own voice. This is why your voice sounds different to you than it does on a recording. You hear your own voice, partly through bone conduction, and partly through air, with the stapedius reducing the airborne component. The middle ear cavity connects to the back of the throat through the eustachian tube, allowing air pressure to equalize on both sides of the eardrum. Normally, this tube is closed, but it opens briefly when you swallow or yawn, when external air pressure changes, as when ascending or descending in an airplane or driving in mountains. The pressure difference across the eardrum can become uncomfortable or even painful until the eustachian tube opens and equalizes it. This is why swallowing or yawning often pops your ears. The inner ear is where mechanical vibration finally becomes neural information. It contains two main structures: the cochlea, responsible for hearing, and the vestibular system, responsible for balance. We'll focus on the cochlea here and return to the vestibular system in the next chapter. The cochlea is a spiral-shaped structure about the size of a pea that makes 2 3/4 turns within the densest bone in the body. If you could uncoil it, the cochlea would be about 35 millimeters long. It's divided lengthwise into 3 fluid-filled chambers by 2 membranes, Reisner's membrane and the basilar membrane. The chamber above Reisner's membrane is the vestibular duct or scala vestibuli. The chamber below the basilar membrane is the tympanic duct or scala tympani. These 2 chambers are filled with perilymph, a fluid similar in composition to other extracellular fluids in the body. Between the 2 membranes is the cochlear duct or scala media, filled with endolymph, which has an unusual composition, high in potassium and low in sodium, more like intracellular fluid. When the stapes pushes against the oval window, it creates pressure waves in the perilymph of the vestibular duct. These waves travel along the cochlea, displacing the basilar membrane as they go. The basilar membrane is not uniform. At the base of the cochlea, near the oval window, it's narrow and stiff. At the apex, the far end, it's wider and more flexible. This gradient in mechanical properties makes the basilar membrane frequency selective. High-frequency sounds cause maximum displacement near the base. Low-frequency sounds travel farther before producing maximum displacement, affecting the membrane more at the apex. This tonotopic organization means that different frequencies are mapped to different locations along the cochlea, a principle that's preserved throughout the auditory pathway all the way to the cortex. Resting on the basilar membrane is the organ of Corti, the actual sensory apparatus of hearing. It contains the hair cells, the mechanoreceptors that transduce mechanical motion into electrical signals. There are 2 types, inner hair cells and outer hair cells, arranged in rows along the length of the cochlea. Inner hair cells, of which there are about 3,500 per ear, are the actual sensory receptors. They're responsible for sending auditory information to the brain. Outer hair cells, much more numerous at around 12,000 per ear, have a different and rather surprising function. They're motor cells, as well as sensory receptors. Each hair cell has a bundle of stereocilia projecting from its top surface. Despite the name, these aren't true cilia. They don't have the internal structure of cilia, but rather are specialized microvilli, elongated cellular projections arranged in rows of graded height. When the basilar membrane moves, the organ of Corti shifts relative to the tectorial membrane, a gelatinous structure that lies above the hair cells. This shearing motion deflects the stereocilia. When stereocilia bend toward the tallest members of the bundle, they're depolarized. When they bend the other direction, they're hyperpolarized. The mechanism is elegant. Tiny protein filaments called tip links connect the tip of each stereocilium to the side of its taller neighbor. When the bundle bends in the excitatory direction, the tip links pull on mechanically gated ion channels, opening them, potassium ions from the endolymph rush into the hair cell. Remember, endolymph has unusually high potassium concentration, and there's a substantial electrical potential across the membrane, about 80 millivolts, with the endolymph side positive. This combination creates a powerful driving force for potassium entry. When the channels open, potassium floods in, depolarizing the cell. This depolarization opens voltage-gated calcium channels at the base of the hair cell. Calcium enters, and this triggers the release of neurotransmitter onto the auditory nerve fibers that synapse with the hair cell. The response is remarkably fast. Hair cells can follow vibrations up to several thousand hertz, responding with temporal precision measured in microseconds. They also have an enormous dynamic range, responding to sounds from the threshold of hearing to levels 120 decibels higher, a million-fold range in sound pressure. The outer hair cells amplify and sharpen the cochlea's frequency selectivity. When depolarized, outer hair cells change length, contracting when depolarized and elongating when hyperpolarized. They do this through a motor protein called prestin embedded in their cell membrane. This electromotility, as it's called, allows outer hair cells to actively amplify basilar membrane vibrations. When a sound causes the basilar membrane to vibrate at a particular location, the outer hair cells there respond by changing length in sync with the vibration, effectively adding energy to the motion and amplifying it. This amplification is frequency specific and only affects quiet sounds. Loud sounds swamp the system, bypassing the amplification. This explains why damage to outer hair cells, which is unfortunately common from noise exposure or certain medications, particularly affects the ability to hear quiet sounds while loud sounds remain audible. The inner hair cells, once stimulated, release glutamate onto the terminals of auditory nerve fibers. Each inner hair cell contacts about 10 nerve fibers, and each nerve fiber contacts only one inner hair cell. This precise one-to-one connectivity preserves frequency information. The auditory nerve, with about 30,000 fibers per ear, carries information to the brainstem. Auditory information follows a complex path through the brainstem, with multiple relay stations on the way to the cortex. The first stop is the cochlear nucleus in the medulla, where different aspects of the auditory signal begin to be processed separately. From there, pathways project to the superior olivary complex, where binaural comparisons between the two ears, first occur. This is the beginning of sound localization, determining where a sound is coming from based on tiny differences in timing and intensity at the two ears. Further up the pathway, the inferior colliculus in the midbrain integrates ascending auditory information and also receives descending input from the cortex. From there, information reaches the medial geniculate nucleus of the thalamus, the auditory relay station, before finally arriving at the primary auditory cortex in the temporal lobe. The primary auditory cortex, located in a region called Heschel's gyrus on the upper surface of the temporal lobe, maintains the tonotopic organization established in the cochlea. Different areas respond best to different frequencies, creating a frequency map across the cortical surface. But the cortex does much more than simply represent frequency. Neurons here are sensitive to complex features of sounds, combinations of frequencies, temporal patterns, modulations in amplitude or frequency. Adjacent areas process increasingly abstract aspects of sound, eventually leading to regions specialized for particular categories of meaningful sounds, like speech or music. Sound localization, Knowing where a sound is coming from relies on comparing the signals arriving at the two ears. For sounds off to one side, the sound wave reaches the near ear before the far ear. This interaural time difference is tiny, at most about 600 microseconds for a sound source directly to one side. Yet the auditory system can detect differences as small as 10 microseconds, allowing accurate localization. For high-frequency sounds, where wavelengths are short, the head creates a sound shadow, making sounds louder at the near ear than the far ear. This interaural intensity difference provides another localization cue. Localization in the vertical plane, distinguishing up from down, front from back, relies on more subtle cues provided by the pinna. The complex shape of the outer ear creates frequency-dependent filtering that varies with sound direction. The brain learns these patterns through experience and uses them to interpret elevation. This is why sounds can seem to come from odd locations when you're wearing earbuds that bypass the pinna's filtering. Hearing provides crucial information beyond simple detection of sounds. It enables communication through speech, one of the defining features of human culture. The auditory system is exquisitely tuned for speech perception, able to extract meaning from the rapid, complex acoustic patterns of spoken language. Specialized regions of the cortex, particularly in the left hemisphere for most people, are devoted to analyzing speech sounds, extracting phonemes, recognizing words, and understanding grammar and meaning. Music, another uniquely human domain, depends entirely on hearing. The emotional power of music, its ability to move us, to evoke memories, to synchronize group behavior, all emerge from the auditory system's analysis of patterns in sound. Pitch, rhythm, melody, harmony, timbre, these are all auditory percepts constructed by the brain from analysis of sound wave properties. Hearing also provides information about the surrounding environment. Footsteps approaching from behind, traffic noise indicating nearby roads, the rustle of leaves suggesting wind, the patter of rain, the crack of breaking branches, the voices of other people. Much of this processing is automatic, below conscious awareness, constantly updating your understanding of your surroundings and alerting you to anything requiring attention. The cocktail party effect demonstrates the sophistication of auditory processing. In a noisy environment with multiple people talking simultaneously, you can focus attention on one voice and follow that conversation while suppressing the others. This selective attention involves both bottom-up processing, the acoustic properties that distinguish different voices, and top-down processing using knowledge of language, context, and expectations to help separate and interpret the signal of interest. Amazingly, the auditory system monitors the unattended channels as well. If someone speaks your name across the room, you'll often notice despite not consciously listening to that conversation. Hearing loss, unfortunately, is common and becomes more prevalent with age. Conductive hearing loss results from problems in the outer or middle ear that prevent sound from reaching the inner ear effectively. This might be as simple as earwax blocking the ear canal, or as complex as otosclerosis, abnormal bone growth that immobilizes the stapes. Conductive losses generally affect all frequencies similarly and can often be helped with amplification or corrected surgically. Sensorineural hearing loss results from damage to the inner ear or auditory nerve. The most common cause is damage to hair cells, particularly outer hair cells, from aging, noise exposure, or ototoxic medications. Unlike conductive loss, sensorineural loss is typically frequency specific, usually affecting high frequencies first. This is why people with age-related hearing loss, presbycusis, often complain that they can hear people talking but can't understand what they're saying. They're missing the high-frequency consonants that carry much of speech's intelligibility. Once hair cells are damaged, they don't regenerate in mammals, though interestingly, birds can regenerate hair cells after damage. This irreversibility makes noise protection important. Sustained exposure to sounds above 85 decibels can cause permanent damage, yet many common activities, concerts, motorcycles, power tools, even loud music through headphones, easily exceed this level. Tinnitus, the perception of sound in the absence of external sound, affects about 15% of adults to some degree. It's often described as ringing, buzzing, or hissing. While tinnitus can result from many causes, it's frequently associated with hearing loss and appears to reflect changes in auditory cortex activity, possibly a form of neural compensation for reduced input from the damaged cochlea. Complete deafness, while much rarer, profoundly affects development, especially if present from birth. Language acquisition, social interaction, and cognitive development all typically depend heavily on auditory input. However, the human capacity for language is not tied exclusively to sound. Sign languages are complete, complex linguistic systems that develop naturally in deaf communities and engage the same brain regions that process spoken language. This demonstrates that language itself is independent of modality. It's the structure and meaning that matter, not whether it's transmitted through sound or vision. Modern cochlear implants can restore a form of hearing to some profoundly deaf individuals by directly stimulating the auditory nerve with electrical signals. A microphone picks up sounds, a processor analyzes them and determines which frequencies are present, and a microphone's flashed in out, and an array of electrodes inserted into the cochlea stimulates different populations of nerve fibers to roughly recreate the tonotopic pattern of activation that natural sound would produce. While the sound quality differs from natural hearing, many users develop excellent speech comprehension, and some can even enjoy music. Hearing, then, is the sense of time made manifest. While vision presents a detailed spatial map of the world in front of you, hearing excels at temporal pattern recognition, tracking events as they unfold over milliseconds to minutes, extracting meaning from the sequential structure of sounds, alerting you to changes even from directions you can't see. It's a sense that operates continuously, even during sleep, maintaining a connection to the environment that vision, which switches off when you close your eyes, cannot match. Yet the inner ear does more than detect sound. The same fluid-filled labyrinth that houses the cochlea also contains the sensors that tell you how your head is positioned and moving through space. These vestibular organs work so seamlessly, so automatically, that most people never think about them until they malfunction. It's to this hidden sense of balance that we turn next, exploring how the inner ear keeps you oriented in space and coordinated in movement. Most people can list 5 senses without hesitation: sight, hearing, touch, taste, smell. These are the traditional 5, the Aristotelian senses recognized for millennia. But the human sensory system includes others, equally important yet less celebrated, senses so automatic and seamlessly integrated into experience that we rarely notice them until they fail. 2 of these hidden senses are equilibrioception, the sense of balance, and proprioception, the sense of body position. Together, they enable you to move through space without falling over, to know where your limbs are without looking at them, to coordinate complex movements without conscious effort. Without them, the simplest actions, walking, reaching, even standing still, would become impossibly difficult. Balance begins in the inner ear, in the vestibular system. This system occupies the space just above and behind the cochlea and consists of two main components, the semicircular canals and the otolithic organs. These structures detect head movement and position relative to gravity, providing the central nervous system with continuous updates about spatial orientation. The three semicircular canals are fluid-filled loops, oriented roughly perpendicular to each other, aligned approximately with the three dimensions of space. One canal detects rotation in the horizontal plane, head turning as if shaking your head no. Another detects rotation in a vertical plane oriented front to back, head nodding as if saying yes. The third detects rotation in a vertical plane oriented side to side, head tilting as if touching ear to shoulder. This three-dimensional arrangement means that any head rotation, regardless of direction, will stimulate at least one canal and usually some combination of all three. Each semicircular canal widens at one end into a bulge called the ampulla. Within the ampulla sits the crista ampullaris, a ridge of tissue topped by a gelatinous mass called the cupula that spans the ampulla like a swinging door. Embedded in the crista are hair cells, similar in structure to the cochlear hair cells, with stereocilia projecting into the cupula. When you rotate your head, the skull and the membranous walls of the canals move with it, but the endolymph fluid inside, due to inertia, lags behind momentarily. This relative motion between canal wall and fluid pushes against the cupula, deflecting it and bending the stereocilia of the hair cells. As in the cochlea, this mechanical deflection opens ion channels, changing the hair cell's membrane potential and altering the rate at which they release neurotransmitter onto vestibular nerve fibers. The semicircular canals are organized in pairs across the two ears. The horizontal canal on the left pairs with the horizontal canal on the right. When you turn your head to the left horizontal canal's hair cells increase their firing rate, while the right horizontal canal's hair cells decrease theirs. The brain compares these signals from the paired canals to determine the direction and speed of head rotation. This push-pull arrangement increases sensitivity and allows the system to work over a wider range of rotation speeds. The otolithic organs, the utricle and saccule, detect linear acceleration and head tilt relative to gravity. Structurally, they're quite different from the semicircular canals. Each contains a patch of hair cells called a macula, with stereocilia projecting into a gelatinous layer topped by a mass of calcium carbonate crystals called otoconia, or colloquially ear stones. These crystals are denser than the surrounding fluid and tissue, giving them inertia. When you tilt your head or accelerate linearly, gravity or inertial forces act on the otoconia, shifting them and the gelatinous layer they're embedded in. This shifts the gelatinous layer relative to the underlying hair cells, bending the stereocilia. The utricle's macula is oriented roughly horizontally and is most sensitive to horizontal accelerations and to head tilt in the pitch and roll planes. The saccule's macula is oriented vertically and responds best to vertical accelerations and to head position in the upright dimension. The vestibular system doesn't work in isolation. It constantly integrates its signals with visual information and somatosensory information from the body, particularly proprioceptive information from the neck, which tells the brain about head position relative to the body. This multisensory integration is essential for maintaining balance and spatial orientation, One crucial function of the vestibular system is the vestibulo-ocular reflex, or VOR. This reflex automatically moves your eyes to compensate for head movement, keeping your gaze stable even when your head is moving. When your head turns to the right, the VOR causes your eyes to turn to the left by an equal amount, keeping the visual world stable on your retinas. This happens automatically, with a latency of only about 10 milliseconds, faster than conscious perception. You can demonstrate the VOR's importance by trying to read while shaking your head. The words remain legible because your eyes are compensating for the head movement. Now try holding your head still and instead shaking the book. The words blur into illegibility, even though the relative motion between your eyes and the book is the same. The VOR only compensates for head movement, not for external motion. The vestibular system also drives postural reflexes that help maintain balance. Information from the vestibular organs reaches the brainstem and cerebellum, where it's integrated with other sensory information and used to generate motor commands that adjust muscle tension throughout the body. When you start to tip to one side, vestibular signals detect this, and reflexive muscle contractions work to restore balance before you consciously register the problem. Proprioception, the other hidden sense, provides information about body position and movement. It's sometimes called kinesthesia, though technically kinesthesia refers specifically to sensing movement, while proprioception includes sensing static position as well. Proprioceptive information comes from mechanoreceptors in muscles, tendons, and joints throughout the body. Muscle spindles are stretch receptors embedded within skeletal muscles, running parallel to the regular muscle fibers. Each muscle spindle contains several specialized muscle fibers called intrafusal fibers, wrapped at their middles by the endings of sensory neurons. When the muscle is stretched, the intrafusal fibers are stretched with it, deforming the sensory endings and triggering action potentials. The rate of firing encodes both the length of the muscle and the speed at which it's changing length. This information travels to the spinal cord and brain, continuously updating your nervous system about muscle length. Golgi tendon organs are located at the junction between muscle and tendon. They're sensitive to muscle tension rather than length. When a muscle contracts and pulls on its tendon, the Golgi tendon organ is compressed, activating its sensory endings. This provides information about how hard a muscle is working, which complements the length information from muscle spindles. Joint receptors in the capsules surrounding joints provide additional information about joint angle and movement. These include several types of mechanoreceptors, rapidly adapting receptors that signal movement, slowly adapting receptors that signal static position, and receptors sensitive to extreme joint angles that may serve a protective function, signaling potentially harmful positions. All of this proprioceptive information flows into the central nervous system, traveling up the spinal cord in the dorsal columns to the brainstem and then to the thalamus and somatosensory cortex. It's also distributed to the cerebellum, which uses proprioceptive feedback to coordinate movement. The remarkable thing about proprioception is how automatic it is. Right now, without looking, you know the position of your limbs, whether your arms are bent or straight, whether your legs are crossed. You can reach out and touch your nose with your eyes closed because proprioception tells you where your finger is and where your nose is. This seems simple until you consider the computational problem involved. To know where your fingertip is in space requires knowing the angles of every joint between your shoulder and your fingertip, integrating all of that into a spatial representation and updating it continuously as you move. Your brain does this effortlessly. in the background without conscious awareness of the complexity involved. Proprioception is essential for motor control. The motor system doesn't just issue commands to muscles and hope for the best. It constantly monitors the results of those commands through proprioceptive feedback, comparing intended movement with actual movement and making corrections. This feedback loop is what allows skilled movement, the precise coordination required for playing a musical instrument, typing, surgery, athletics, or any complex motor task. The cerebellum plays a crucial role in integrating proprioceptive information with motor commands. Damage to the cerebellum produces ataxia, a lack of coordination characterized by movements that are poorly controlled, overshooting or undershooting intended targets. People with cerebellar damage often develop a wide-based stumbling gait and have difficulty with tasks requiring precise timing or coordination. When proprioception itself is impaired, the results can be even more dramatic. Some neurological conditions damage the sensory nerves carrying proprioceptive information or the dorsal columns of the spinal cord where these signals travel. People with severe proprioceptive loss report feeling disconnected from their bodies, having to watch their limbs to know where they are. Walking becomes a visual task, requiring constant attention. In darkness or with eyes closed, movement becomes nearly impossible. This reveals how much we normally rely on proprioception, continuously and unconsciously. The vestibular system and proprioception work together to create spatial awareness and guide movement. When you walk, proprioception tells you about the position and movement of your legs, while the vestibular system monitors your head's position and movement. Vision adds information about the external environment. The brain integrates all three, creating a coherent sense of where you are in space and how you're moving through it. This integration can be disrupted, producing illusions or disorientation. Motion sickness results from conflict between sensory systems. When you're reading in a car, your vestibular system detects the vehicle's acceleration and turning, but your eyes, focused on the stationary book, see no motion. This sensory conflict, visual and vestibular systems providing incompatible information, is thought to trigger nausea through mechanisms that may have evolved to cause vomiting in response to neurotoxins, which can also produce sensory disturbances. Spinning creates a different form of disorientation. When you spin continuously in one direction, the endolymph in your horizontal canals accelerates and eventually catches up with the rotation of the canals themselves. The cupula returns to its resting position, and the sensation of spinning fades, even though you're still rotating. When you suddenly stop, the endolymph continues moving due to inertia, deflecting the cupula in the opposite direction. This creates the sensation that you're now spinning the other direction, even though you're stationary. The VOR, faithfully responding to the vestibular signal, moves your eyes as if you were spinning, producing the characteristic oscillating eye movements called nystagmus that occur after spinning stops. The visual world appears to spin, and the conflict between visual and vestibular signals can produce nausea. Vertigo, the sensation that you or your surroundings are spinning when there's no actual motion, typically results from vestibular system dysfunction. Benign paroxysmal positional vertigo, or BPPV, the most common cause of vertigo, occurs when otoconia become dislodged from the otolithic organs and migrate into one of the semicircular canals. These crystals, moving with head position changes, inappropriately stimulate the canal, creating false signals of rotation. The result is intense vertigo, often accompanied by nausea, triggered by specific head positions like rolling over in bed or looking up. Meniere's disease produces episodic vertigo, hearing loss, and tinnitus, thought to result from abnormal endolymph fluid dynamics in the inner ear. Vestibular neuritis, inflammation of the vestibular nerve, usually following a viral infection, produces sudden severe vertigo that gradually improves over days to weeks as the brain adapts to the reduced vestibular input from the affected side. These conditions, unpleasant as they are, highlight how essential the vestibular system is for normal function. When it fails, even temporarily, the result is profoundly disabling. You can't walk straight, can't focus your vision due to loss of the VOR, feel nauseated, and lose all sense of spatial orientation. This demonstrates that balance is not something that just happens. It requires constant active sensing and motor adjustment, normally so automatic you never think about it. Astronauts in orbit experience a peculiar form of vestibular confusion. In microgravity, there's no consistent direction of gravitational pull to orient the otolithic organs. The signals from the vestibular system become ambiguous, no longer reliably indicating which way is up. This produces space motion sickness in about half of astronauts during their first few days in orbit. Interestingly, the brain adapts fairly quickly, learning to rely more on visual cues and less on vestibular information. When astronauts return to Earth, they experience another period of disorientation as the brain readapts to having meaningful gravitational cues again. Both balance and proprioception are senses we only appreciate when we consider their absence. They operate continuously, automatically, below conscious awareness, providing essential information that enables normal movement and spatial awareness. They're integrated so seamlessly with vision and motor control that they feel like part of the background, not senses at all, but simply part of the basic ability to inhabit and control a body. Yet they are senses, with specialized receptor cells, dedicated neural pathways, and specific brain regions for processing their information. They detect real physical properties of the world: acceleration, gravity, tension, stretch. They translate these physical properties into neural signals and conscious perception. In this, they're fundamentally the same as vision and hearing, detecting different aspects of physical reality and constructing your experience of it. The senses we've explored so far, vision, hearing, balance, proprioception, all detect physical forces: photons, sound waves, gravity, mechanical tension. The remaining senses, taste and smell, operate differently. They detect chemicals, specific molecules dissolved in saliva or floating in air. These chemosensory systems identify substances by their molecular structure, a form of perception that seems more intimate, more direct. You don't detect chemicals at a distance the way you see or hear. You must make contact, ingest, or inhale. This intimacy makes the chemical senses particularly powerful triggers of memory and emotion, as we'll explore next, beginning with taste. Taste, or gustation as it's properly called, is the sense that analyzes chemicals dissolved in saliva, identifying substances entering the mouth, and informing decisions about whether to swallow or spit them out. While we often think of taste as contributing to the pleasure of eating, its primary biological function is more utilitarian, distinguishing nutritious from toxic, safe from dangerous. Taste is, fundamentally, a guardian sense, the last checkpoint before substances enter the body. The tongue is the primary organ of taste, though taste receptors are found in other locations as well, including the soft palate, the pharynx, the upper esophagus, and even the epiglottis. The tongue itself is a muscular organ covered with stratified squamous epithelium and studded with numerous small bumps visible to the naked eye. These bumps are the papillae, and it's on these structures that most taste buds reside. There are four types of papillae. Filiform papillae are the most numerous, giving the tongue's surface its slightly rough texture. Despite their prominence, filiform papillae contain no taste buds. They're purely mechanical in function, helping to manipulate food and providing friction for breaking up food particles. The other three types do contain taste buds. Fungiform papillae are mushroom-shaped structures scattered across the front two-thirds of the tongue, most concentrated at the tip and edges. Each contains several taste buds. Foliate papillae are located on the lateral edges of the tongue toward the back, appearing as a series of ridges and grooves. They contain numerous taste buds, particularly in children, though these diminish in number with age. Circumvallate papillae are the largest and least numerous, typically numbering between 7 and 12, arranged in a V-shaped row across the back of the tongue just in front of the sulcus terminalis, the groove that marks the boundary between the oral and pharyngeal parts of the tongue. Each circumvallate papilla is surrounded by a trench, and the walls of both papilla and trench are densely packed with taste buds, hundreds per papilla. A taste bud is not a single cell, but an organized cluster of about 50 to 100 cells, including several different cell types. The taste receptor cells themselves are modified epithelial cells, not neurons, though they synapse with sensory neurons that carry taste information to the brain. These receptor cells are organized rather like the sections of an orange, extending from the base of the taste bud to its apex, where their tips form a taste pore opening onto the tongue's surface. Dissolved tastants enter this pore and contact the microvilli, projecting from the receptor cells, initiating the transduction process. Taste receptor cells come in several types based on their molecular machinery and what they respond to. Type 2 cells respond to sweet, bitter, and umami tastes. Type 3 cells respond to sour tastes. Type 1 cells appear to play supporting roles, maintaining the ionic environment and perhaps detecting salty tastes, though the mechanism for salt detection remains somewhat controversial. Humans can detect 5 basic taste qualities: sweet, salty, sour, bitter, and umami. This number might seem surprisingly small given the rich variety of flavors we experience, but remember that most of what we think of as flavor is actually smell, which we'll discuss in the next chapter. Taste itself is limited to these 5 categories, though within each category there's variation in intensity and nuance. Sweet taste is triggered by sugars and other molecules with similar structures, including some amino acids and small proteins. The biological significance is clear. Sweet usually indicates carbohydrates, a concentrated source of calories. Sweetness is inherently pleasant, motivating consumption of these energy-rich foods. The receptor for sweet taste is a heterodimer, a protein complex made of 2 different subunits called T1R2 and T1R3. When a sweet molecule binds to this receptor, it activates a G protein signaling cascade that ultimately increases calcium inside the cell, triggering neurotransmitter release. Interestingly, artificial sweeteners, which have very different chemical structures from sugars, nonetheless bind to this same receptor, activating it without providing any calories, a molecular hack that the diet industry depends upon. Umami, meaning delicious or savory in Japanese, is the taste of glutamate, an amino acid that's a building block of proteins. Glutamate in food indicates protein content, making umami another marker of nutritious substances. The umami receptor is also a heterodimer, T1R1 and T1R3. Note that it shares one subunit with the sweet receptor. This might explain why some compounds can taste both sweet and umami, and why these two taste qualities can sometimes influence each other. Foods rich in umami include aged cheeses, tomatoes, mushrooms, soy sauce, and meat broths. Monosodium glutamate, or MSG, much maligned in some circles, is simply the sodium salt of glutamic acid and is a potent umami tastant. Bitter taste is more complex. Rather than a single receptor, there are about 25 different bitter receptors in humans, each responding to different bitter compounds. This makes sense given that bitter taste serves primarily as a poison detection system. Many toxic substances, particularly plant alkaloids that plants produce as defenses against being eaten, taste intensely bitter. Having multiple bitter receptors increases the range of toxins that can be detected. All bitter receptors are called T2Rs, and like sweet and umami receptors, they work through G protein signaling cascades. The intensity of bitter perception varies considerably among individuals due to genetic differences in bitter receptor genes. The classic example involves phenylthiocarbamide, or PTC, and the related compound PROP. Some people find these intensely bitter, others moderately bitter, and some barely taste them at all. This variation results from different versions of the TAS2R38 gene. People with two copies of the sensitive version are supertasters for these compounds. People with two copies of the insensitive version are non-tasters. Heterozygotes fall in between. Being a supertaster for bitter compounds influences food preferences. Supertasters often dislike vegetables like Brussels sprouts, kale, and broccoli, which contain bitter compounds. They may drink their coffee with more sugar or avoid it entirely. They tend to prefer less bitter, less complex flavors generally. On the population level, the frequency of different TAS2R38 variants varies across ethnic groups, likely reflecting different selective pressures from the local plant toxins in ancestral environments. Sour taste detects acids, which dissociate to release hydrogen ions in solution. The hydrogen ions directly enter the taste receptor cell through ion channels, lowering the pH inside the cell and triggering a cascade that leads to neurotransmitter release. The intensity of sour taste correlates with acidity. Citric acid in lemons, acetic acid in vinegar, lactic acid in yogurt all produce sour taste. Mild sourness can be pleasant and appetite stimulating. Intense sourness is aversive, likely because extreme acidity indicates spoilage or fermentation that has gone too far. Salty taste in its pure form detects sodium chloride, table salt. Sodium is essential for nerve and muscle function, and the body actively regulates sodium levels. Moderate salt taste is pleasant and motivates consumption when sodium levels are low. Excessive saltiness becomes unpleasant. The receptor for sodium appears to be a simple sodium channel that allows sodium ions to enter the taste receptor cell directly, depolarizing it. However, other salts, particularly those containing potassium, magnesium, or calcium, can also produce salty sensations, sometimes with a bitter or metallic edge, suggesting that multiple mechanisms may contribute to salty taste perception. The traditional tongue map, which assigns different tastes to different regions of the tongue, sweet at the tip, bitter at the back, sour on the sides, and so forth, is largely myth. While there are minor variations in sensitivity across the tongue's surface, all taste qualities can be detected everywhere taste buds are present. Every taste bud contains cells responsive to multiple, if not all, taste qualities. The tongue map myth apparently arose from a misinterpretation of research published in the early 20th century and has persisted in textbooks and popular culture despite being thoroughly debunked. Once taste receptor cells are activated, they must transmit this information to the brain. Unlike most sensory receptors, taste cells are not themselves neurons. Instead, they synapse onto the peripheral processes of sensory neurons, whose cell bodies reside in ganglia outside the tongue. Three cranial nerves carry taste information, dividing up the territory. The facial nerve, cranial nerve 7, specifically its branch called the chorda tympani, carries taste information from the front two-thirds of the tongue. This nerve also carries taste information from the soft palate. The glossopharyngeal nerve, cranial nerve 9, handles the posterior third of the tongue, including the circumvallate papillae. The vagus nerve, cranial nerve 10, carries taste information from the throat, epiglottis, and upper esophagus. These nerves converge on the nucleus of the solitary tract in the medulla, the brainstem's taste processing center. From the nucleus of the solitary tract, taste information projects to the thalamus, specifically to the ventral posterior medial nucleus, and from there to the primary gustatory cortex in the insula and frontal operculum. This cortical region is where taste sensations become conscious. Adjacent cortical areas integrate taste with smell, texture, temperature, and other aspects of eating experience, contributing to flavor perception, which we'll explore in more detail in a later chapter. Taste perception is not simply a readout of receptor activity. The brain actively interprets taste signals, influenced by experience, expectation, and context. The same taste can be perceived differently depending on whether you expect it. A sweet taste in a food context is pleasant. The same sweetness in something you expect to be savory, like meat, might be off-putting. Cultural learning plays a huge role. Tastes that are pleasant in one culture might be aversive in another. Consider fermented foods, which range from mildly to intensely sour and often have complex, sometimes bitter or umami notes. Some cultures prize them, others avoid them. Taste preferences change over time through exposure. Children typically show neophobia, wariness of new foods, and preferences for sweet and salty tastes while avoiding bitter. This makes evolutionary sense. Sweet indicates safe calories, bitter often indicates toxins, and children, being more vulnerable, benefit from being cautious. With repeated safe exposure, bitter foods can become accepted and even preferred. Coffee, beer, dark chocolate, many vegetables, all acquired tastes for many people, initially off-putting but learn to be enjoyed. The number of taste buds decreases with age. Infants have taste buds not only on the tongue, but scattered throughout the oral cavity, numbering perhaps 10,000 inches total. By adulthood, this has dropped to around 5,000 to 6,000, concentrated on the tongue and palate. In older adults, the number continues to decline, and the remaining taste buds become less sensitive. This contributes to complaints that food tastes bland and can reduce appetite, with consequences for nutrition. Taste can be temporarily or permanently altered by various factors. Medications can affect taste, either by being secreted into saliva, where they directly stimulate taste receptors, or by altering the receptors themselves. Chemotherapy drugs are notorious for producing dysgeusia, distorted taste perception, often described as metallic or unpleasant. Head trauma can damage the cranial nerves carrying taste information, particularly if the fracture involves the temporal bone through which the facial nerve passes. Upper respiratory infections can affect taste, though this is usually because they affect smell, and what's perceived as taste loss is actually smell loss. Some people experience burning mouth syndrome, a chronic condition characterized by burning pain in the mouth, often the tongue, sometimes accompanied by taste disturbances. The cause remains poorly understood, but may involve damage to small nerve fibers in the oral mucosa. True taste disorders, where the taste system itself is primarily affected, are less common than smell disorders, but can significantly impact quality of life and nutrition. Taste also interacts with other sensory systems in complex ways. Texture influences taste perception. The same flavoring in a smooth versus grainy texture can taste different. Temperature matters too. Cold suppresses sweet and bitter perception, which is why soft drinks and ice cream taste much sweeter at room temperature than when cold. Astringency, the puckering sensation from tannins in tea or red wine, isn't actually a taste, but a tactile sensation mediated by trigeminal nerve fibers in the mouth. Similarly, the burn of chili peppers or the cooling of menthol are not tastes but pain or temperature sensations. Color influences taste perception through learned associations. If you color lemon lime soda red, people tend to taste cherry or strawberry, even though the actual flavoring hasn't changed. The brain expects certain colors to correspond to certain flavors and sometimes lets expectation override sensory input. This is why food industry scientists carefully match colors to flavors, and why uncolored or unusually colored foods can seem odd or unappetizing even when they taste fine. Sound can even influence taste. Research has shown that people perceive potato chips as crunchier and fresher when the sound of their own chewing is amplified. High-pitched sounds can enhance perception of sweetness, while low-pitched sounds enhance bitterness. The mechanisms behind these cross-modal interactions are not fully understood, but likely involve learned associations and the brain's tendency to integrate multisensory information into coherent perceptions. Taste serves several important functions beyond simply making food pleasant. It initiates the cephalic phase of digestion, the preparatory responses that begin before food reaches the stomach. Tasting sweet or savory food triggers saliva production, stomach acid secretion, and release of digestive enzymes. These anticipatory responses prime the digestive system for the incoming meal, improving digestion efficiency. Taste also provides feedback during eating, influencing how much you consume. Sweet taste activates reward pathways in the brain, particularly circuits involving dopamine, which motivate continued eating. This made sense in ancestral environments where concentrated calories were scarce. In modern environments with unlimited access to highly sweetened foods, this system can drive overconsumption. Salt and umami similarly activate reward circuits, though typically less intensely than sweet. Bitter taste, in contrast, can inhibit eating. If something tastes sufficiently bitter, the reflexive response is to spit it out, a protective mechanism that presumably prevented our ancestors from ingesting toxins. However, this protection is far from perfect. Many modern toxins, including most synthetic poisons, are tasteless, and some naturally occurring toxins don't taste sufficiently bitter to be rejected, particularly if masked by other flavors. The genetics of taste perception reveal interesting evolutionary patterns. The number and variety of bitter receptors vary considerably across species. Herbivores, who face a much wider array of plant defensive compounds than carnivores, tend to have more bitter receptor genes. Humans, as omnivores, fall in between. Even within humans, the number of functional bitter receptor genes varies. Some genes have become pseudogenes, non-functional versions, in some individuals or populations. This variation suggests that different bitter sensitivities were advantageous in different environments. The selective pressure on taste systems likely varied with diet. Populations that historically consumed primarily meat would face fewer plant toxins and might tolerate loss of some bitter sensitivity. Populations with plant-heavy diets would benefit from maintaining broad bitter detection capabilities. Modern genetic studies are beginning to map out these patterns, revealing how human taste perception has been shaped by dietary history. Taste, then, is far more than a simple pleasure system, though it certainly contributes to the enjoyment of eating. It's a sophisticated chemical analysis system, identifying substances based on their molecular properties and using those identifications to guide behavior. It motivates consumption of nutrients, warns against toxins, initiates digestive processes, and provides feedback that regulates intake. Working mostly automatically, beneath conscious analysis, taste shapes food preferences, dietary choices, and ultimately nutrition and health. It's a sense we engage with multiple times per day, every day of our lives, yet often give little thought to until it fails or until we pause to truly attend to the sensations it provides. But taste, as complex as it is, provides only part of what we experience when eating. The richness of flavor, the full sensory experience of food, depends critically on another chemical sense that operates through a different route. Smell, or olfaction, detects volatile compounds released from food as you chew and breathe, contributing most of what you perceive as flavor. It's a sense even more sensitive than taste, capable of detecting thousands of distinct odors and one with peculiar power over memory and emotion. We turn our attention to this remarkable sense next. Smell, or olfaction, operates through chemical detection like taste, but it samples the air rather than substances dissolved in saliva. Volatile molecules, small enough to evaporate and float through air, enter the nasal cavity with each breath and encounter specialized receptor neurons that translate molecular structure into neural signals. These signals travel not through the thalamus, like most sensory information, but directly to ancient brain regions involved in emotion and memory. This direct connection helps explain smell's peculiar ability to evoke vivid recollections and powerful emotional responses, why a particular scent can transport you instantly to a specific moment in your past with an immediacy that visual or auditory memories rarely match. The olfactory system begins in the nasal cavity, the air-filled space behind the nose, divided by the nasal septum into left and right chambers. Most of the nasal cavity is lined with respiratory epithelium, whose job is to warm, humidify, and clean incoming air, not to detect odors. The olfactory epithelium, the actual sensory tissue, occupies only a small region high in each nasal cavity, a patch of specialized tissue, perhaps 2 to 3 square centimeters in area. Its position, up near the roof of the nasal cavity, means that normal quiet breathing doesn't bring much air directly to it. When you sniff, actively inhaling through your nose with a sharper inhalation than normal breathing, you create turbulent airflow that directs more air upward to the olfactory epithelium. This is why you sniff when trying to smell something. The olfactory epithelium contains three main cell types: olfactory receptor neurons, which are the actual sensory cells, supporting cells, which provide structural and metabolic support, and basal cells, which are stem cells that can differentiate into new olfactory receptor neurons. This last point is remarkable. Olfactory receptor neurons are one of the few types of neurons in the adult human nervous system that are continuously replaced. Each olfactory receptor neuron has a lifespan of only 30 to 60 days before it dies and is replaced by a new one generated from the basal stem cells. This regenerative capacity likely evolved because the olfactory neurons are directly exposed to the external environment and are thus vulnerable to damage from pathogens, toxins, and simple mechanical insult. An olfactory receptor neuron is a bipolar neuron, meaning it has two distinct processes extending from the cell body. One process, the dendrite, extends to the surface of the epithelium, where it expands into a knob from which numerous cilia project. These cilia, unlike motile cilia that beat to move mucus or fluids, are non-motile sensory structures. They lie embedded in a layer of mucus covering the epithelium, and it's on these cilia that the olfactory receptors themselves are located. The other process, the axon, extends upward through the cribriform plate, a region of the skull's ethmoid bone that's perforated with numerous small holes. These axons, thousands of them bundled together, constitute the olfactory nerve, cranial nerve 1. On the brain side of the cribriform plate, the axons enter the olfactory bulb, the first brain structure in the olfactory pathway. Olfactory receptors are proteins embedded in the membrane of the cilia. Each is a G protein coupled receptor, similar in basic structure to many other sensory and neurotransmitter receptors. When an odorant molecule floating through the air and dissolved in the mucus layer encounters a receptor to which it can bind, it activates the receptor. The activated receptor triggers a G protein signaling cascade that ultimately opens ion channels, allowing sodium and calcium to enter the neuron. This depolarizes the cell, and if the depolarization is sufficient, action potentials are generated that travel down the axon to the olfactory bulb. The human genome contains approximately 400 functional olfactory receptor genes, though the exact number varies slightly among individuals because some genes are pseudogenes, non-functional versions, in some people. This number might seem large, and indeed it represents the largest gene family in the mammalian genome, yet it's substantially smaller than in many other mammals. Mice have over 1,000 functional olfactory receptor genes. Dogs have around 800. The reduction in humans likely reflects decreased selective pressure on olfaction as vision became increasingly dominant in primate evolution. Each olfactory receptor neuron expresses only one type of olfactory receptor from this library of 400. This means that each neuron is sensitive to a specific set of odorant molecules, those whose molecular features fit the binding pocket of that particular receptor. This specificity is not absolute. Most olfactory receptors can bind multiple related molecules, and most odorant molecules can bind multiple receptors. The combinatorial coding that results allows the olfactory system to discriminate among thousands, perhaps tens of thousands, of distinct odors, despite having only 400 receptor types. How exactly do olfactory receptors recognize odorant molecules? The traditional shape theory proposes that each receptor detects specific molecular shapes, with the odorant fitting into the receptor's binding pocket like a key into a lock. This model has considerable support. Molecules with similar shapes often smell similar, and alterations to a molecule's shape can change how it smells. However, shape isn't the whole story. Enantiomers, mirror image versions of the same molecule with identical shapes but different handedness, can sometimes smell different, suggesting that more than just gross shape matters. The weak shape, or odotope theory, suggests that receptors recognize specific molecular features, fragments, or aspects of the odorant molecule rather than its overall shape. An odorant might activate several receptors, each responding to a different feature, and the brain combines these partial recognitions to identify the overall molecule. This combinatorial approach could explain how relatively few receptors can identify so many different odors. A more controversial theory, vibration theory, proposes that olfactory receptors detect not shape, but vibrational frequencies of chemical bonds within odorant molecules. This theory attempts to explain why some molecules with very different shapes smell similar and why isotopic substitution, replacing hydrogen with deuterium, for instance, can sometimes alter perceived smell despite producing no change in shape. The mechanism proposed involves quantum tunneling of electrons, decidedly exotic physics for a biological sensory system. While intriguing, vibrational theory remains disputed, with some experimental results supporting it and others contradicting it. Regardless of the precise mechanism, odorant binding activates olfactory receptor neurons, which send signals to the olfactory bulb. The organization within the bulb is elegant and systematic, all olfactory receptor neurons expressing the same receptor type, which are scattered randomly across the olfactory epithelium, send their axons to the same glomerulus in the olfactory bulb. A glomerulus is a spherical structure where the axons from receptor neurons synapse onto the dendrites of output neurons called mitral cells and tufted cells. There are about 2,000 glomeruli per olfactory bulb, which means that signals from approximately 25,000 receptor neurons, all expressing the same receptor, converge onto each glomerulus. This convergence amplifies weak signals. If only a few odorant molecules activate only a few neurons, their combined input to the glomerulus might still be sufficient to activate the mitral cells. This contributes to olfaction's remarkable sensitivity. For some odorants, humans can detect concentrations as low as a few parts per trillion. Trained perfumers or wine tasters can distinguish among thousands of distinct smells. Even untrained individuals can identify characteristic odors with great reliability. Coffee, roses, gasoline, cinnamon, each produces a distinctive pattern of glomerular activation. From the glomeruli, mitral and tufted cells project to several brain regions, collectively called the olfactory cortex. Unlike other sensory systems, olfactory information does not relay through the thalamus before reaching the cortex. This direct projection to cortex is unusual and reflects olfaction's evolutionary antiquity. The primary target is the piriform cortex, located on the underside of the frontal and temporal lobes. The piriform cortex performs pattern recognition, identifying characteristic combinations of receptor activation that correspond to particular odors. Olfactory information also projects directly to the amygdala, involved in emotional processing, and to the entorhinal cortex, which is part of the hippocampal formation involved in memory. These connections explain why smells so effectively evoke emotions and memories. A scent associated with a past event can trigger vivid recollection of that event, along with the emotions you felt at the time. This phenomenon, sometimes called the Proust effect, after the famous literary example in Marcel Proust's In Search of Lost Time, where the taste and smell of a Madeleine cake triggers an elaborate childhood memory, is a common human experience. The mechanism underlying smell's connection to memory involves the hippocampus, which binds together disparate elements of an experience: what you saw, heard, felt, smelled, where you were, who you were with, into a unified memory. Because olfactory information reaches the hippocampus directly without thalamic relay, odors may be particularly strongly encoded in these episodic memories. Later, encountering the same smell reactivates the entire memory trace, bringing back not just the fact of the event, but the subjective experience of it, what it felt like to be there. Olfaction also projects to the orbitofrontal cortex, particularly to regions involved in representing the reward value or pleasantness of sensory experiences. This is where odor perception becomes conscious and where you become aware not just that something has a smell, but whether that smell is pleasant, unpleasant, or neutral. Hedonic value, the pleasantness or unpleasantness of an odor, is not entirely hardwired. Some smells, like fecal odors or those of decay, are nearly universally unpleasant, likely for good, evolutionary reasons. Others vary substantially based on experience and culture. Smells associated with pleasant experiences become pleasant. Smells associated with unpleasant experiences or illness become aversive. This learned association allows olfactory preferences to be shaped by experience. Human olfactory perception varies considerably among individuals. Some variation is genetic. The genes encoding olfactory receptors are highly polymorphic, meaning there are many different versions of each gene in the population. If you have a non-functional version of a particular receptor gene, you'll be unable to smell the compounds that receptor detects, a condition called specific anosmia. One well-studied example involves androstenone, a steroid compound found in male sweat. Approximately 30 to 50% of people cannot smell it at all. Among those who can, some describe it as pleasant, musky, even sexy, while others find it unpleasant, smelling like urine or sweat. These differences correlate with genetic variations in the receptor gene that detects androstenone. Age affects olfactory perception. Olfactory sensitivity peaks in young adulthood and declines gradually thereafter. By age 65, a significant fraction of people have measurable olfactory impairment, and by 80, more than half show substantial loss. This decline results from several factors: reduction in the number of olfactory receptor neurons, changes in the olfactory bulb and cortex, and possibly reduced ability to regenerate olfactory neurons from stem cells. Olfactory loss in elderly populations is more than an inconvenience. It affects appetite, food enjoyment, and nutrition. It also eliminates an important warning system for detecting spoiled food, gas leaks, smoke, and other environmental hazards. Complete loss of smell, anosmia, can result from head trauma that severs the olfactory nerves as they pass through the cribriform plate, from upper respiratory infections that damage the olfactory epithelium, from chronic sinusitis that blocks airflow to the olfactory region, or from neurodegenerative diseases. Anosmia profoundly affects quality of life. Food loses most of its flavor, becoming bland and uninteresting. The emotional richness that smells bring to experience is lost. Many anosmic individuals report feeling disconnected from their environment and from memories, as though a dimension of experience has been removed. Interestingly, anosmia or reduced olfactory function can be an early sign of certain neurodegenerative diseases, appearing years before other symptoms. In Parkinson's disease, olfactory testing can detect impairment before the characteristic motor symptoms appear. In Alzheimer's disease, olfactory deficits are common and may reflect early pathology in olfactory cortex and hippocampus. This has led to interest in olfactory testing as a potential early screening tool for these conditions. Some individuals experience parosmia, a condition where odors are perceived but distorted, often smelling unpleasant, regardless of what they actually are. This can occur following upper respiratory infections or head trauma and may reflect disordered regeneration of olfactory receptor neurons, with axons connecting to inappropriate glomeruli. Phantasmia, perceiving smells that aren't present, can result from epileptic activity in olfactory cortex or from other neurological causes. The vomeronasal organ, or VNO, is a structure separate from the main olfactory system found in many mammals. It's located in the nasal septum and detects pheromones, chemical signals involved in social and reproductive behavior. In mice, the VNO plays crucial roles in mating behavior, aggression, and maternal behavior. In humans, the situation is less clear. Human fetuses have a VNO that appears functional, but in adults, the structure is vestigial, often not clearly identifiable, and probably not functional. Whether humans detect pheromones at all, and if so, through what mechanism, remains controversial. Some studies suggest that human body odors can influence mood, mate selection, or menstrual synchrony, but the evidence is mixed and the mechanisms uncertain. Smell plays roles beyond conscious odor perception. It contributes to flavor perception during eating, a topic we'll explore in detail in the next chapter. It influences behavior and emotion, often without conscious awareness. The smell of a place, a person, even a season, contributes to the overall feeling of being in that environment. Aromatherapy, while scientifically controversial regarding specific therapeutic claims, does demonstrate that pleasant odors can affect mood, reduce stress, and enhance relaxation, at least for some individuals in some contexts. Olfaction also provides information about other people, though this operates largely unconsciously in humans. This distinction is more than academic. When you have a cold and complain that food has no taste, what's actually happened is that nasal congestion has blocked retronasal airflow. Your taste system works fine, but without retronasal smell, flavor collapses to just the basic tastes. The rich complexity that makes chocolate taste like chocolate, strawberry like strawberry, coffee like coffee, all of that is olfactory. The brain regions responsible for integrating taste and smell into flavor include the orbitofrontal cortex, located just above the eye sockets. Neurons here receive both gustatory and olfactory input, and many respond to both. These multimodal neurons are thought to represent flavor itself, the integrated perception that's more than the sum of taste and smell. Damage to orbitofrontal cortex can impair flavor perception while leaving basic taste and smell intact, producing a syndrome where patients can detect individual sensory components but don't bind them into normal flavor experience. Beyond taste and smell, texture profoundly influences flavor perception. The mouthfeel of food, its texture and consistency as you chew and swallow, is detected by mechanoreceptors in the mouth, tongue, and throat. These include the same types of receptors found in skin elsewhere on the body. Meissner's corpuscles detecting light touch, Pacinian corpuscles detecting pressure and vibration, Merkel cells detecting sustained pressure. The distribution of these receptors in the oral cavity creates high tactile sensitivity. Your tongue can detect texture details that your fingertips would miss. Food texture has its own vocabulary: creamy, crunchy, crispy, chewy, smooth, rough, grainy, velvety. Each textural quality creates a different pattern of mechanoreceptor activation. Crunchy foods generate sound, as well as vibration and varying pressure as they fracture. These acoustic signals contribute to the perception of freshness and quality. Stale chips that have absorbed moisture lose their crunch and become less appealing, even though their taste might be unchanged. Research has shown that amplifying the sound of chewing makes potato chips seem crunchier and fresher. Fat creates a distinctive mouthfeel, a smooth, rich, coating sensation that's independent of taste or smell. While fat itself is largely flavorless, it carries fat-soluble flavor compounds and creates a textural perception that's highly rewarding. This has led to debate about whether fat should be considered a sixth taste. Some research suggests specialized receptors on taste cells can detect fatty acids, and there may be a gustatory component to fat perception. But much of what we perceive as fattiness is textural, mediated by tactile receptors. Temperature is another crucial component of flavor experience. The same food tastes different at different temperatures. This is partly because taste receptors themselves are temperature sensitive. Cold suppresses sweet and bitter perception, which is why soft drinks and ice cream are formulated to taste sweeter at serving temperature than they do at room temperature. When they warm up, they often taste cloyingly sweet. Proteins that create umami taste are more easily extracted and detected at higher temperatures, which is why hot broth has more intense, savory flavor than cold. But temperature also acts as a sensory dimension in its own right. Cold, hot, and room temperature each create different sensations that become part of the flavor experience. Ice cream isn't just sweet and creamy, it's also cold, and that coldness is integral to what ice cream is. Hot soup, hot coffee, these require heat to be perceptually complete. Temperature is detected by thermoreceptors, which are free nerve endings in the oral mucosa that express temperature-sensitive TRP ion channels. Trigeminal sensations add yet another dimension. The trigeminal nerve, cranial nerve 5, provides somatosensory innervation to the face and mouth. Its free nerve endings detect chemical irritants, producing sensations that are technically not tastes or smells, but something else: chemesthesis. The burn of chili peppers comes from capsaicin, which activates TRPV1 receptors, the same receptors that detect painful heat. This is why capsaicin literally feels hot, even though it doesn't change food temperature. Similarly, the coolness of menthol comes from activation of TRPM8 receptors, which normally detect cold temperatures. Menthol makes your mouth feel cold, even though nothing has cooled. The tingling of carbonation comes from carbon dioxide activating pain receptors. The pungency of horseradish, mustard, or wasabi comes from isothiocyanate compounds activating TRPA1 receptors, creating a burning sensation in the nose and sinuses that's distinctly different from the mouth burn of capsaicin. The astringent drying sensation of tannins in tea or red wine comes from tannins precipitating proteins in saliva and oral mucosa, creating a textural change detected by mechanoreceptors. receptors. These trigeminal sensations are not flavors in the strict sense, but they're experienced as part of flavor. Spicy food isn't just flavorful, it's an experience that includes controlled pain. That pain, for those who enjoy spicy food, becomes pleasurable through mechanisms that are not entirely understood, but may involve endorphin release and learned association between the pain and the pleasurable food context. Vision influences flavor through several mechanisms. First, appearance provides expectation. The color, shape, and presentation of food create predictions about what it will taste like. If these expectations are met, flavor perception is normal. If they're violated, by coloring lemon lime soda red, for instance, the mismatch between expected and actual flavor creates confusion and can alter perception. People often report tasting what they expected based on color rather than what's actually there, at least initially. Second, vision affects appetite and willingness to try foods. Brightly colored fruits and vegetables are often more appealing than dull colored ones, signaling ripeness and nutrient content. Brown or gray foods, unless they're expected to be those colors like bread crust or chocolate, can seem less appealing because those colors often indicate decay or burning. The visual presentation of food on a plate, what chefs call plating, influences not just whether you want to eat it, but how you perceive its quality and flavor. Third, there's evidence for direct cross-modal effects, where visual properties influence gustatory and olfactory perception. The brain's flavor representation appears to weight visual input as evidence about what's being consumed, and this can shift the balance of detected flavors. A drink colored orange red tastes more orange flavored than the same drink without color, even to experienced tasters who are aware of the manipulation. Sound contributes to flavor experience in ways beyond the obvious crunch and crackle of certain foods. The ambient sound environment affects taste perception. Studies have shown that loud noise suppresses sweetness and saltiness perception while enhancing umami. This may explain why airplane food often seems bland. The loud cabin noise measurably reduces taste sensitivity. Airlines compensate by over-seasoning food or emphasizing umami-rich ingredients like tomato juice, which passengers often find surprisingly appealing at altitude. Even music influences flavor perception. High-pitched music seems to enhance sweetness perception, while low-pitched music enhances bitterness. Fast-tempo music can make food seem more refreshing, while slow music makes it seem more filling and substantial. These effects are subtle and not fully understood, but they demonstrate that flavor perception is not a simple readout of tongue and nose receptors. It's actively constructed by the brain from all available sensory information. The integration of all these sensory inputs into unified flavor experience occurs primarily in the orbitofrontal cortex. This brain region receives converging input from gustatory, olfactory, somatosensory, visual, and auditory cortices. Individual neurons here respond to multiple sensory modalities. Some respond to particular combinations, sweet taste, combined with floral smell, for instance, or fatty texture combined with savory taste. These combination-sensitive neurons may represent specific foods or flavor categories. The orbitofrontal cortex also represents the reward value or pleasantness of flavors, which changes based on physiological state. When you're hungry, flavors are more pleasant and rewarding. As you eat and become sated, the same flavors become less pleasant. This is called sensory-specific satiety, and it's adaptive. It encourages dietary variety, by making you less interested in continuing to eat the same food, even if you still have appetite for different foods. The orbitofrontal cortex tracks this changing reward value, with neurons that respond strongly to a food when you're hungry, but progressively less as you eat it to satiety. Individual differences in flavor perception are substantial. Beyond genetic variation in taste and smell sensitivity, people vary in their oral anatomy, the number and distribution of taste buds, the surface area of olfactory epithelium, the density of tactile receptors. They vary in cognitive factors like attention, memory, and expectations. They vary enormously in experience and culture, which shape flavor preferences and the vocabulary available for describing flavors. Some people are super tasters, with more taste buds than average and correspondingly more intense taste perception. They tend to find many foods too intensely flavored and often avoid bitter vegetables, strong coffee, alcohol, and very spicy foods. Others are non-tasters, with fewer taste buds and less intense taste perception. They may prefer stronger, more intensely flavored foods and be more adventurous eaters. Cultural learning plays a massive role in flavor preferences. Almost all flavor preferences, beyond the basic liking for sweet and dislike for intensely bitter, are learned through experience. What's delicious in one culture may be disgusting in another. Fermented fish, aged cheese, durian fruit, various insects, organ meats, all are prized in some cultures and avoided in others. These preferences are typically established in childhood through repeated exposure and social learning. The phenomenon of acquired tastes demonstrates this plasticity. Coffee, beer, wine, many vegetables, and spicy foods are often initially unpleasant, especially to children. With repeated exposure in positive social contexts, they become tolerated and eventually preferred. The neural basis likely involves learning associations in the orbitofrontal cortex and amygdala, where flavor representations are linked to outcome predictions. If a flavor repeatedly predicts positive outcomes, nourishment, social bonding, pleasure, it acquires positive valence. Flavor can also become aversive through learning, particularly through a powerful mechanism called conditioned taste aversion. If you eat a novel food and then become ill, even hours later, you'll often develop a strong aversion to that food that can last for years. This happens even if you consciously know the food didn't cause the illness. The mechanism evolved to protect against eating poisonous foods, which often produce delayed illness. In modern contexts, it can lead to unfortunate aversions to foods that happen to be eaten before illness from other causes. Context profoundly influences flavor experience. The same food tastes better when eaten in a pleasant environment, with good company, from attractive dishes. This is not just psychological overlay on unchanged sensory perception. The context actually alters the neural representation of flavor in the orbitofrontal cortex. The pleasure of food is partly intrinsic to the food itself, but partly constructed by the brain based on the entire context of consumption. Expectations shape flavor experience powerfully. If you expect food to taste good, it often does. If you expect it to taste bad, it often does, even if the actual sensory input is identical. Price can influence perceived quality, with the same wine tasting better when people believe it's expensive than when they believe it's cheap. Brand names influence perceived taste. Packaging and presentation matter. These expectation effects are not simply people lying or conforming to social pressure. Brain imaging shows that expected quality changes the neural response to food in reward regions. The multisensory nature of flavor explains why eating disorders, sensory impairments, and neurological conditions can dramatically affect food experience. Loss of smell, whether from aging, head trauma, or COVID-19 infection, which has brought anosmia to widespread public attention, eliminates most of flavor, making food uninteresting and reducing appetite. Some people with anosmia report that eating becomes a purely functional activity, consuming calories without pleasure. Taste loss, less common but still significant, similarly degrades flavor. Even partial loss, like reduced bitter sensitivity, can shift food preferences. Changes in texture perception, which can occur with dental problems, oral surgery, or neurological conditions affecting tactile sensation, also alter food experience. Dysphagia, difficulty swallowing, can make eating anxious and unpleasant, even if flavor perception remains intact. On the other hand, pregnancy can temporarily alter flavor perception, sometimes creating aversions to previously enjoyed foods or cravings for unusual combinations. The mechanisms aren't fully understood, but likely involve hormonal effects on chemosensory systems and changes in the brain's flavor evaluation circuitry, perhaps evolved to influence dietary choices during pregnancy. Flavor is also central to social life in ways that go beyond simple nutrition. Sharing food is a human universal, present in every culture. Meals structure social time, bringing people together. Food traditions carry cultural identity and memory across generations. The ability to enjoy food together, to share flavor experiences and preferences, creates social bonds. When flavor perception is impaired, people often report feeling socially isolated, unable to participate fully in an important aspect of human interaction. The food industry's deep understanding of multisensory flavor has led to sophisticated manipulation of food properties to maximize appeal. Flavor scientists adjust not just taste and smell, but also texture, color, sound, temperature, and even packaging to influence perception. They create what's been called hyperpalatable foods, combinations of salt, sugar, fat, and texture designed to maximally activate reward circuits, often in ways that promote overconsumption. This can be seen as exploitation of evolved preferences for calorie-dense foods, preferences that were adaptive in environments where such foods were scarce, but can drive excessive intake in modern environments where they're ubiquitous and cheap. Understanding flavor as a multisensory constructed perception rather than a simple chemical readout helps explain why these manipulations are so effective. The brain's flavor system evolved to evaluate foods based on all available cues. Modern food engineering exploits that by optimizing all the cues simultaneously. Mindful eating practices encourage paying attention to flavor, slowing down to notice all the sensory dimensions of food, taste, smell, texture, temperature, sound. This can increase enjoyment, improve satiety signals, and promote healthier eating patterns. When you attend fully to flavor, you often need less food to feel satisfied. The richness of the sensory experience itself becomes rewarding, not just the calories. Flavor, then, is not a single sense, but an integrated multisensory experience. It combines information from taste, smell, touch, temperature, pain, vision, hearing, and cognitive factors like memory, expectation, and context. This integration happens seamlessly, automatically, producing a unified perception that feels simple despite its computational complexity. Flavor shapes not just what you eat, but your social relationships, cultural identity, and daily pleasure. It's a sense, or more accurately, a constructed perception that you engage with multiple times every day that's essential to survival, and that, when functioning well, provides some of life's most reliable and accessible pleasures. Having explored the chemical senses of taste and smell and their integration into flavor, we now turn to the body's largest sensory organ, the skin. Touch, or more properly, the somatosensory system, provides a wealth of information through an array of specialized receptors distributed across your entire body surface. It's to this tactile sense, the sense of physical contact with the world, that we turn our attention next. The skin is the body's largest organ, covering approximately 1.5 to 2 square meters in an average adult and accounting for about 15% of total body weight. It's also one of the most complex, serving multiple essential functions: protection against pathogens and physical injury, prevention of water loss, regulation of body temperature, synthesis of vitamin D, immune surveillance, and sensory reception. This last function, providing information about physical contact with the environment, is our focus here. But to understand how skin senses touch, temperature, and pain, we must first understand its structure. Skin consists of two main layers, the epidermis and the dermis. Below these lies the hypodermis or subcutaneous tissue, which, while not technically part of the skin, provides important structural and insulative functions. Each layer has distinct properties and contributes differently to sensory function. The epidermis is the outermost layer, composed of stratified squamous epithelium. It contains no blood vessels and receives nutrients by diffusion from the underlying dermis. The primary cell type is the keratinocyte, which produces the protein keratin that gives skin its protective properties. The epidermis also contains melanocytes, which produce the pigment melanin that provides some protection from ultraviolet radiation, and Langerhans cells, which are part of the immune system and help defend against pathogens that breach the skin barrier. The epidermis is organized into distinct layers or strata. The deepest is the stratum basal, a single layer of stem cells that continuously divide to produce new keratinocytes. These newly formed cells are pushed upward by subsequent cell divisions below them, beginning a journey to the skin surface that takes about 4 weeks. As they ascend, they differentiate, changing in structure and function. Above the basale is the stratum spinosum, several cell layers thick, where cells begin producing keratin and forming strong connections to their neighbors through desmosomes. Then comes the stratum granulosum, where cells accumulate dense granules of keratin and lipids. Here, cells begin to die, their nuclei and organelles breaking down. The stratum lucidum, present only in thick skin like palms and soles, is a thin, clear layer of dead, flattened cells packed with keratin. Finally, the outermost layer is the stratum corneum, composed of 10 to 30 layers of dead, flat, keratin-filled cells called corneocytes. These dead cells, bound together by lipids, create a waterproof protective barrier that keeps pathogens out and body fluids in. Cells at the surface are continuously shed through a process called desquamation, with the entire stratum corneum replaced roughly every 2 weeks. You shed approximately 30,000 to 40,000 dead skin cells per minute, nearly 50 million per day. Much of household dust consists of shed skin cells. This continuous renewal is essential for maintaining barrier function. It also means that superficial injuries to the epidermis heal quickly without scarring, as the damaged tissue is simply replaced through the normal differentiation process. Only when injury extends into the dermis, damaging structures that don't regenerate fully, does scarring occur. The dermis lies below the epidermis and is composed of connective tissue rich in collagen and elastin fibers. Collagen provides tensile strength, preventing the skin from tearing under stress. Elastin provides elasticity, allowing skin to stretch and return to its original shape. The dermis contains blood vessels that nourish the epidermis, lymphatic vessels that collect excess fluid, and immune cells, hair follicles, sweat glands, sebaceous glands, and most importantly for our purposes, sensory receptors. The dermis divides into two layers. The upper papillary layer consists of loose, connective tissue arranged in small projections called dermal papillae that extend into the overlying epidermis. These projections increase surface area for nutrient exchange and create the patterns of ridges visible on fingertips and palms, your fingerprints. The papillary layer contains many capillaries and is where many tactile receptors reside. The deeper reticular layer consists of dense, irregular connective tissue with thicker collagen and elastin fibers. It's this layer that gives skin most of its strength and elasticity. The boundary between papillary and reticular layers is not sharp but gradual. Both contain sensory receptors, with different receptor types concentrated at different depths. The hypodermis beneath the dermis consists primarily of loose connective tissue and adipose tissue, body fat. It anchors the skin to underlying structures like muscle and bone, provides insulation, and serves as an energy store. The thickness of the hypodermis varies greatly across body regions and among individuals. It's much thicker in the buttocks and abdomen than in the eyelids or back of the hand. Some sensory receptors, particularly those detecting deep pressure, are located in the hypodermis. Skin thickness varies across the body. Thick skin, found on palms and soles, has all 5 epidermal layers, including a prominent stratum lucidum, a thick stratum corneum, and no hair follicles. Thin skin, which covers most of the body, lacks the stratum lucidum, has a thinner stratum corneum, and contains hair follicles. Despite these names, the dermis is actually thicker in thin skin than in thick skin. The terms refer to the epidermis alone. The distribution of sensory receptors also varies across body regions, creating dramatic differences in tactile sensitivity. Your fingertips, lips, tongue, and genitals have very high receptor density and correspondingly acute tactile sensitivity. You can discriminate fine details, detect light touches, and precisely localize stimuli in these regions. Your back, upper arms, and thighs have much lower receptor density and correspondingly lower sensitivity. This uneven distribution makes functional sense. You interact with the world primarily through your hands and mouth, which benefit from high sensitivity, and regions like your back, which rarely interact delicately with objects, function adequately with lower sensitivity. This sensitivity variation is reflected in the brain. The primary somatosensory cortex contains a distorted map of the body surface called the sensory homunculus. Body regions with high receptor density occupy disproportionately large cortical areas. The representation of your hand is vastly larger than the representation of your back, even though the back has more total skin area. This cortical magnification means that more neural resources are devoted to processing information from sensitive body regions, enhancing their discriminative abilities. Skin also houses structures beyond sensory receptors. Hair follicles, found everywhere except palms, soles, and a few other specialized regions, produce hair that varies in thickness from the fine vellus hair covering most of the body to the coarse terminal hair of the scalp, eyebrows, and after puberty, various other regions. Each hair follicle is surrounded by nerve endings that detect hair movement, effectively extending the skin's tactile sensitivity beyond its surface. When something brushes against a hair, bending it, you feel it before it touches your skin. Erector pili muscles attach to hair follicles. When these smooth muscles contract, they pull the hair erect and create a small bump on the skin surface, goosebumps. In furry mammals, this response fluffs up the coat, trapping more air for insulation when cold or making the animal appear larger when threatened. In relatively hairless humans, it's vestigial, producing goosebumps but little functional benefit. The response is triggered by cold or by emotional states like fear, mediated by the sympathetic nervous system. Sebaceous glands, associated with most hair follicles, secrete sebum, an oily mixture of lipids and cellular debris. Sebum waterproofs and moisturizes the skin and hair, prevents drying and cracking, and has some antibacterial properties. Sebaceous gland activity increases dramatically at puberty under the influence of androgens, which explains the oily skin and acne common in adolescence. Overactive sebaceous glands or blocked follicles can produce acne, while underactive glands contribute to dry skin. Sweat glands come in two types with different functions and distributions. Eccrine sweat glands are distributed across almost the entire body surface, particularly dense on palms, soles, and forehead. They produce watery sweat, composed mostly of water with small amounts of salt, urea, and other waste products. Eccrine sweat's primary function is thermoregulation. When body temperature rises, sweat production increases. The sweat spreads across the skin's surface and evaporates, removing heat through the latent heat of vaporization. This evaporative cooling is essential for temperature regulation during exercise or in hot environments. Eccrine glands are controlled by the sympathetic nervous system, but unusually, they use acetylcholine rather than norepinephrine as their neurotransmitter. They can produce up to several liters of sweat per hour during intense exercise in hot conditions, though this requires adequate hydration to sustain. Chronic exposure to hot climates produces adaptation. Sweat becomes more dilute, conserving salt, and sweating becomes more efficient. Apocrine sweat glands develop at puberty and are located primarily in the armpits and groin. They produce a thicker secretion containing proteins and lipids. This secretion is initially odorless, but bacterial action breaks it down, producing characteristic body odor. Apocrine glands are activated not by heat, but by emotional stress, particularly fear or sexual arousal. Their function in humans is unclear, but in other mammals, similar glands produce pheromones. They may be evolutionary remnants of scent marking or signaling systems. Nails, covering the tips of fingers and toes, are modifications of the epidermis. They consist of heavily keratinized cells forming a hard plate. Nails protect the fingertips from mechanical damage and, by providing a firm backing, enhance tactile sensitivity. The fingertip's soft tissue can deform against the nail, increasing the mechanical advantage for discriminating fine details. Nails also assist in fine manipulation, scratching, and grooming. The nail plate grows from the nail matrix at the base, hidden under skin. The visible white semicircle at the nail base, the lunula, is part of the matrix where keratinization is not yet complete. The nail bed beneath the nail plate is richly supplied with blood vessels, giving the nail its pink color. Damage to the nail matrix can produce permanent nail deformities, while damage to the nail plate alone is temporary as the nail grows out and is replaced. Skin color results primarily from melanin produced by melanocytes in the stratum basale. There are two types of melanin: eumelanin, which is brown to black, and pheomelanin, which is red to yellow. The ratio of these and the total amount of melanin determine skin color. All humans have similar numbers of melanocytes. Variation in skin color results from differences in melanin production and distribution, not melanocyte number. Melanin absorbs ultraviolet radiation, providing protection against DNA damage that can lead to skin cancer. Darker skin contains more melanin and provides better UV protection. This is adaptive in regions near the equator with intense sun exposure. Lighter skin evolved in populations living at higher latitudes where UV radiation is less intense. Lighter skin allows more UV penetration, which is necessary for vitamin D synthesis. Vitamin D deficiency can cause rickets and other health problems, creating selective pressure for lighter skin in low UV environments. Skin is also immunologically active. Beyond its physical barrier function, it contains numerous immune cells. Langerhans cells in the epidermis capture antigens and present them to T cells, initiating adaptive immune responses. Mast cells in the dermis release histamine and other mediators during allergic reactions and inflammation. Dermal dendritic cells and lymphocytes patrol for pathogens. The skin is not just a passive barrier, but an active component of the immune system. Blood flow through dermal capillaries serves both nutritive and thermoregulatory functions. In cold conditions, arteriovenous shunts direct blood away from the skin surface, conserving core body heat. The skin becomes pale and cold. In hot conditions or during exercise, these shunts close, forcing blood through surface capillaries where it can release heat. The skin becomes flushed and warm. This vascular control, combined with sweating, allows humans to maintain stable core temperature across a wide range of environmental conditions. Skin aging involves multiple changes. The epidermis thins, becoming more fragile. The dermis loses collagen and elastin, reducing strength and elasticity. Skin becomes looser, less able to return to its original shape after stretching, producing wrinkles and sagging. The hypodermis thins, particularly in the face and hands, reducing cushioning. Wound healing slows. Sensory receptor density may decrease, reducing tactile sensitivity. Sebaceous and sweat gland activity often decreases, producing drier skin. Much of this aging is intrinsic, programmed by genetics, but environmental damage, particularly from UV radiation, accelerates it. Chronic sun exposure damages collagen and elastin, causes hyperpigmentation, producing age spots, and dramatically increases skin cancer risk. Smoking also accelerates skin aging through multiple mechanisms. Protecting skin from excessive UV exposure and avoiding smoking are the most effective ways to slow visible skin aging. The skin, then, is far more than a simple wrapper. It's a complex, metabolically active organ that protects, regulates temperature, synthesizes vitamins, provides immune defense, and serves as a sensory interface with the physical world. The sensory aspect, while just one of many functions, is crucial for interaction with the environment. Through specialized receptors embedded at various depths within this layered structure, skin detects pressure, vibration, texture, temperature, and pain. These receptors, and the remarkable sensitivity and diversity of information they provide, are what we'll explore next. beginning with the mechanoreceptors that detect touch and pressure. Touch is not a single sense, but a collection of related sensory systems that detect mechanical stimulation of the skin. Different types of mechanoreceptors respond to different aspects of touch: light pressure, deep pressure, vibration, stretch, texture. Together, they provide rich information about physical contact with objects and surfaces, enabling everything from crude awareness that something is touching you to the exquisite fine motor control required for surgery or playing a musical instrument. Mechanoreceptors transduce mechanical energy into neural signals. When the skin is deformed by pressure or vibration, mechanically gated ion channels in the receptor's membrane open, allowing ions to flow in and depolarizing the cell. If this depolarization reaches threshold, action potentials are generated and propagate along the sensory neuron to the spinal cord and ultimately the brain. Four main types of mechanoreceptors in glabrous skin, the hairless skin of palms, soles, and fingertips, are responsible for most of our discriminative touch. Each type has distinct properties, responds to different stimuli, and contributes different information. Meissner's corpuscles are located in the dermal papillae, just beneath the epidermis. They're elongated encapsulated receptors, 20 to 40 micrometers wide and up to 150 micrometers tall, consisting of flattened support cells stacked horizontally with nerve terminals woven between them. The entire structure is surrounded by a connective tissue capsule. Meissner's corpuscles are most concentrated in fingertips, palms, lips, tongue, face, nipples, and external genitalia, regions requiring high tactile sensitivity. These receptors are rapidly adapting, meaning they respond vigorously when a stimulus first contacts the skin and again when it's removed, but they quickly stop responding if the stimulus remains constant. This makes them ideal for detecting changes in contact. When you first touch something, when something moves across your skin, when you release contact, they respond best to low-frequency vibrations, roughly 10 to 50 Hertz, and to light, localized touch. Meissner's corpuscles are essential for texture perception. When you run your finger across a textured surface, the ridges and valleys of your fingerprints cause the skin to vibrate at frequencies related to the texture's spatial frequency and your finger's speed. Meissner's corpuscles detect these vibrations, and the brain interprets the pattern as texture. They also contribute to grip control. When you hold an object, Meissner's corpuscles detect small slips that occur before you lose grip entirely, triggering reflexive adjustments in grip force before the object falls. The density of Meissner's corpuscles decreases with age, particularly after age 50, which may contribute to age-related declines in tactile sensitivity and fine motor control. They're also sensitive to vibration from specific medications and to neuropathies that affect small nerve fibers. Pacinian corpuscles are the largest tactile receptors visible to the naked eye at up to 2 millimeters in length. They're located deep in the dermis and in the subcutaneous tissue, as well as in connective tissue associated with joints, bones, and some internal organs. Structurally, they consist of a nerve ending surrounded by multiple concentric layers of flattened cells separated by fluid, resembling a tiny onion. These corpuscles are rapidly adapting and respond to deep pressure and high-frequency vibration, roughly 200 to 300 Hertz. The layered structure acts as a mechanical filter. When pressure is first applied, the layers compress, deforming the central nerve ending and triggering a burst of action potentials. But if the pressure continues steadily, the layers redistribute the force and the nerve ending returns to its resting state. When pressure is released, the layers expand, again deforming the nerve ending and producing another burst of activity. Pacinian corpuscles are exquisitely sensitive to vibration. They can detect vibrations with amplitudes of less than 1 micrometer, smaller than a bacterial cell. This sensitivity makes them important for detecting vibrations transmitted through objects you're holding. When using a tool, Pacinian corpuscles in your hand detect vibrations that provide information about what the tool is contacting. They allow you to feel through a tool, extending your tactile sense beyond your skin. They're also important for detecting distant events. When something drops on a floor or table, the vibration travels through the structure and can be detected by Pacinian corpuscles in your hand or foot, alerting you to the event before you hear or see it. This rapidly acting vibration sense may have evolved to detect approaching predators or prey through ground vibrations. Merkel cells, technically Merkel cell neurite complexes, are located in the basal epidermis, particularly concentrated in fingertips and other highly sensitive regions. Unlike other mechanoreceptors, the sensory component involves not just the neuron, but specialized epithelial cells called Merkel cells. The nerve terminal forms a disc-shaped expansion that closely opposes the Merkel cell, and neurotransmitter-containing vesicles in the Merkel cell suggest it may actively participate in transduction. Merkel cells are slowly adapting, meaning they continue to respond as long as pressure is applied. They respond to sustained indentation of the skin and have small, well-defined receptive fields, making them excellent for spatial resolution. They're responsible for fine spatial discrimin and texture perception, particularly for statically touching surfaces rather than moving across them. Two-point discrimination, the ability to perceive two nearby points of contact as separate rather than single, depends heavily on Merkel cells. On your fingertips, where Merkel cells are dense, you can distinguish points separated by just 2 to 3 millimeters. On your back, where they're sparse, you might need 40 to 50 millimeters of separation. This variation in acuity creates the differential sensitivity map across the body surface. Merkel cells also contribute to edge detection and shape perception. When you press your finger against an edge, Merkel cells on either side of the edge respond differently, creating a sharp transition in neural activity that the brain interprets as an edge. The entire structure is surrounded by a connective tissue capsule. Meissner's corpuscles are most concentrated in fingertips, palms, lips, tongue, face, nipples, and external genitalia, regions requiring high tactile sensitivity. These receptors are rapidly adapting, meaning they respond vigorously when a stimulus first contacts the skin and again when it's removed, but they quickly stop responding if the stimulus remains constant. This makes them ideal for detecting changes in contact. When you first touch something, when something moves across your skin, when you release contact, they respond best to low-frequency vibrations, roughly 10 to 50 Hz, and to light, localized touch. Meissner's corpuscles are essential for texture perception. When you run your finger across a textured surface, the ridges and valleys of your fingerprints cause the skin to vibrate at frequencies related to the texture's spatial frequency and your finger's speed. Meissner's corpuscles detect these vibrations, and the brain interprets the pattern as texture. They also contribute to grip control. When you hold an object, Meissner's corpuscles detect small slips that occur before you lose grip entirely, triggering reflexive adjustments in grip force before the object falls. The density of Meissner's corpuscles decreases with age, particularly after age 50, which may contribute to age related declines in tactile sensitivity and fine motor control. They're also sensitive to vibration from specific medications and to neuropathies that affect small nerve fibers. Pacinian corpuscles are the largest tactile receptors visible to the naked eye at up to 2 millimeters in length. They're located deep in the dermis and in the subcutaneous tissue, as well as in connective tissue associated with joints, bones, and some internal organs. Structurally, they consist of a nerve ending surrounded by multiple concentric layers of flattened cells separated by fluid resembling a tiny onion. These corpuscles are rapidly adapting and respond to deep pressure and high frequency vibration, roughly 200 to 300 hertz. The layered structure acts as a mechanical filter. When pressure is first applied, the layers compress, deforming the central nerve ending and triggering a burst of action potentials. But if the pressure continues steadily, the layers redistribute the force and the nerve ending returns to its resting state. When pressure is released, the layers expand, again deforming the nerve ending and producing another burst of activity. Pacinian corpuscles are exquisitely sensitive to vibration. They can detect vibrations with amplitudes of less than 1 micrometer, smaller than a bacterial cell. This sensitivity makes them important for detecting vibrations transmitted through objects you're holding. When using a tool, Pacinian corpuscles in your hand detect vibrations that provide information about what the tool is contacting. They allow you to feel through a tool, extending your tactile sense beyond your skin. They're also important for detecting distant events. When something drops on a floor or table, the vibration travels through the structure and can be detected by Pacinian corpuscles in your hand or foot, alerting you to the event before you hear or see it. This rapidly acting vibration sense may have evolved to detect approaching predators or prey through ground vibrations. Merkel cells, technically Merkel cell neurite complexes, are located in the basal epidermis, particularly concentrated in fingertips and other highly sensitive regions. Unlike other mechanoreceptors, the sensory component involves not just the neuron, but specialized epithelial cells called Merkel cells. The nerve terminal forms a disc-shaped expansion that closely opposes the Merkel cell, and neurotransmitter-containing vesicles in the Merkel cell suggest it may actively participate in transduction. Merkel cells are slowly adapting, meaning they continue to respond as long as pressure is applied. They respond to sustained indentation of the skin and have small, well-defined receptive fields, making them excellent for spatial resolution. They're responsible for fine spatial discrimin and texture perception, particularly for statically touching surfaces rather than moving across them. Two-point discrimination, the ability to perceive two nearby points of contact as separate rather than single, depends heavily on Merkel cells. On your fingertips, where Merkel cells are dense, you can distinguish points separated by just 2 to 3 millimeters. On your back, where they're sparse, you might need 40 to 50 millimeters of separation. This variation in acuity creates the differential sensitivity map across the body surface. Merkel cells also contribute to edge detection and shape perception. When you press your finger against an edge, Merkel cells on either side of the edge respond differently, creating a sharp transition in neural activity that the brain interprets as an edge. Touch adaptation occurs when you maintain contact with a stimulus. Rapidly adapting receptors like Meissner's corpuscles stop responding within a second, which is why you quickly stop noticing your clothing. Slowly adapting receptors like Merkel cells continue responding but with reduced intensity. This adaptation allows the tactile system to remain sensitive to changes, new contacts, or movements, while ignoring constant, unchanging stimulation. Lateral inhibition, where active receptors suppress the responses of neighboring receptors, sharpens tactile perception. This neural mechanism enhances edges and contrast, making it easier to detect boundaries and discontinuities. It's similar to lateral inhibition in vision, where it enhances edges in visual images. The result is that your perceived tactile image is sharper than the raw receptor activity would suggest. Tactile illusions demonstrate that touch, like vision, involves active interpretation by the brain. The cutaneous rabbit illusion involves delivering a sequence of taps to the forearm. If taps are delivered first near the wrist, then near the elbow, subjects perceive them as hopping up the arm like a rabbit, even though no taps occurred in between. The brain interpolates based on temporal and spatial patterns. The Aristotle illusion involves crossing your fingers and touching a single object like a small ball. It feels like two objects. This occurs because the sides of your fingers that are touching the ball are normally on opposite sides of the finger and wouldn't simultaneously contact the same object. The brain interprets simultaneous activation of these skin regions as indicating two objects. These illusions aren't failures but reveal the inferential nature of perception. The brain uses past experience to interpret sensory input, making reasonable assumptions that usually work but can be fooled by unusual stimulus configurations. Touch is profoundly important for social bonding and emotional well-being. Gentle touch activates not just discriminative mechanoreceptors, but also C-tactile afferents, unmyelinated nerve fibers that respond best to slow, gentle stroking at skin temperature, typical of affectionate touch. These afferents project to emotional processing regions in the brain rather than to discriminative touch areas, suggesting they mediate the emotional aspect of touch. Affectionate touch reduces stress, promotes bonding between parents and infants, and communicates emotion between individuals. Lack of touch, particularly in infancy and childhood, can have serious developmental consequences. The tactile sense is not just about object manipulation and discrimination, it's fundamental to social connection and emotional health. Touch also has a powerful attentional component. Unexpected touch immediately captures attention. This makes sense evolutionarily. Something touching you might be a threat or an opportunity and requires immediate assessment. Even when touch is expected, attending to tactile sensations enhances perception. Signals from the same receptors produce larger cortical responses when you're paying attention than when you're distracted. The mechanoreceptors of touch, with their diversity, sensitivity, and broad distribution, provide a rich channel of information about physical interaction with the world. They enable manipulation, exploration, recognition, and communication. They work seamlessly with motor systems to produce skilled action. They contribute to emotional experience and social connection. Touch is, in every sense, how we stay in contact with reality, continually updated through millions of receptors about what's physically present, what's pressing against us, what we're pressing against. It's the sense that confirms the physical world's existence moment to moment, giving substance and solidity to experience. Yet mechanoreceptors tell only part of touch's story. The skin also contains thermoreceptors that detect temperature and nociceptors that detect potentially harmful stimulation, warning us of danger. These complementary systems, Temperature sense and pain share the skin with mechanoreceptors but serve different functions and work through different mechanisms. To these, we turn our attention next, exploring how skin detects hot and cold, pleasure and pain. Touch is not a single sense, but a collection of related sensory systems that detect mechanical stimulation of the skin. Different types of mechanoreceptors respond to different aspects of touch: light pressure, deep pressure, vibration, stretch, texture. Together, they provide rich information about physical contact with objects and surfaces, enabling everything from crude awareness that something is touching you to the exquisite fine motor control required for surgery or playing a musical instrument. Mechanoreceptors transduce mechanical energy into neural signals. When the skin is deformed by pressure or vibration, mechanically gated ion channels in the receptor's membrane open, allowing ions to flow in and depolarizing the cell. If this depolarization reaches threshold, action potentials are generated and propagate along the sensory neuron to the spinal cord and ultimately the brain. Temperature and pain are distinct sensations, yet they're closely related. Both are detected by free nerve endings in the skin. Both can signal danger, and they sometimes interact in complex ways, as when extreme heat or cold produces pain. Together, they complement the mechanoreceptors we've just explored, adding dimensions of sensation that are essential for protection and comfort. Temperature sensation begins with thermoreceptors, specialized free nerve endings that respond to warming or cooling. Unlike mechanoreceptors with their elaborate encapsulated structures, thermoreceptors are simply the branching terminals of sensory neurons ending in the dermis and epidermis. What makes them temperature sensitive is the expression of specific ion channels that open or close in response to temperature changes. These channels belong to the TRP, transient receptor potential, family. Different TRP channels have different temperature activation ranges, creating a system that can detect temperatures from painfully cold to painfully hot. TRPM8 channels activate at cool temperatures, roughly 8 to 28 degrees Celsius, producing the sensation of coolness. TRPV3 and TRPV4 activate at warm temperatures, around 30 to 40 degrees Celsius, producing warmth sensation. TRPV1 and TRPV2 activate at hot temperatures, above 43 degrees Celsius, producing heat sensation that blends into pain at higher temperatures. TRPA1 activates at very cold temperatures, below about 17 degrees Celsius, producing cold sensation that becomes painful below about 15 degrees. When temperature changes, these channels open, allowing cations to flow into the nerve ending, depolarizing it. If depolarization reaches threshold, action potentials are generated and travel along the sensory neuron to the spinal cord. The brain interprets the pattern of activity across different thermoreceptor types to determine temperature. Moderate activation of TRPM8 channels signals pleasant coolness. Strong activation signals cold. Activation of TRPV3/4 signals warmth, while TRPVone half activation signals heat. Thermoreceptors are not evenly distributed. Cold receptors are more numerous than warm receptors, and both are concentrated in certain regions. The face, particularly around the nose and mouth, has high thermoreceptor density. Fingertips are moderately sensitive. The trunk has lower sensitivity. This distribution makes functional sense. You sample food temperature with your lips before committing to swallowing, and you explore environmental temperatures with your hands. Temperature perception is relative rather than absolute. thermoreceptors adapt to steady temperatures, becoming less responsive over time. When you first enter a swimming pool, the water might feel cold. After a few minutes, you adapt, and it feels neutral. This adaptation explains why the same stimulus can feel different depending on your skin's starting temperature. The classic demonstration involves 3 bowls of water, one hot, one room temperature, one cold. Put your right hand in hot water and left hand in cold water for a minute. Then put both hands in the room temperature water. It feels cool to your right hand and warm to your left, even though it's the same temperature. Your thermoreceptors are comparing current temperature to recent temperature history rather than providing an absolute readout. Thermoreceptors also show spatial contrast effects. A warm stimulus surrounded by cool skin feels warmer than it would if surrounded by warm skin. This contrast enhancement, similar to simultaneous contrast in vision or lateral inhibition in touch, sharpens temperature perception. The comfortable temperature range for skin is fairly narrow, roughly 30 to 36 degrees Celsius. Within this range, thermal sensation is neutral or pleasant. Outside this range, discomfort increases. Below about 15 degrees or above about 45 degrees, temperature sensation becomes painful. Hayes limits reflect the temperatures at which tissue damage begins to occur. Extreme cold can cause frostbite. Extreme heat causes burns. The transition from temperature to pain serves a protective function, motivating withdrawal before serious damage occurs. Thermal pain involves nociceptors as well as thermoreceptors. Nociceptors are specialized sensory neurons that detect noxious or potentially tissue-damaging stimuli. The term comes from the Latin nocere, to harm. Different nociceptor types respond to different dangerous stimuli. Mechanical nociceptors detect intense mechanical force, like crushing or cutting. Thermal nociceptors detect extreme heat or cold, and polymodal nociceptors respond to multiple stimulus types, including mechanical, thermal, and chemical irritants. Nociceptors are free nerve endings, structurally indistinguishable from thermoreceptors. What makes them nociceptors is their activation threshold and their molecular equipment. They express TRP channels and other receptors that activate only at stimulus intensities that threaten tissue damage. TRPV1, for instance, activates at temperatures above 43 degrees Celsius, right around where heat becomes painful. It also responds to capsaicin, the compound in chili peppers, which is why capsaicin produces a burning sensation. The burn is real at the neural level. Capsaicin is activating the same channels that detect damaging heat. Similarly, TRPM8, which normally detects cool temperatures, responds to menthol. Menthol makes your mouth feel cool, even though temperature hasn't changed. TRPA1, activated by noxious cold, also responds to irritants like mustard oil and cigarette smoke, producing painful tingling or burning sensations. Pain signals travel via 2 types of nerve fibers with different properties. A delta fibers are thinly myelinated, conduct relatively quickly at 5 to 30 meters per second, and mediate first pain or fast pain. This is the sharp, well-localized pain you feel immediately upon injury. It's brief and informative, telling you precisely where you're injured and motivating immediate withdrawal. C fibers are unmyelinated, conduct slowly at 0.5 to 2 meters per second, and mediate second pain or slow pain. This is the dull, aching, burning pain that emerges after first pain is less well localized and persists. It's the throbbing ache after you stub your toe or the burning sensation of a cut. Second pain is thought to promote healing behaviors like immobilization and protection of the injured area. This dual pain system is adaptive. Fast pain produces immediate withdrawal from harmful stimuli. Slow pain motivates continued protective behavior. If you touch a hot stove, fast pain makes you pull your hand away within milliseconds. Slow pain makes you keep your hand still and protected while it heals, avoiding further injury. Pain signals enter the spinal cord and synapse in the dorsal horn, a region specialized for processing nociceptive information. From here, multiple pathways ascend to the brain. The spinothalamic tract carries pain and temperature information to the thalamus and then to somatosensory cortex, providing the discriminative aspect of pain, where it is, how intense, what type. The spinoreticcular and spinomesencephalic tracts project to brainstem and midbrain regions involved in arousal and emotional response, producing the unpleasant affective aspect of pain. Pain is not simply a sensory signal like touch or vision. It's inherently unpleasant, inherently motivating. This affective dimension is crucial to pain's function. Animals with lesions that eliminate the unpleasantness of pain while preserving the sensory detection can recognize painful stimuli but don't avoid them, leading to repeated injury. Pain must be aversive to serve its protective function. The brain processes pain in a distributed network, including somatosensory cortex, insular cortex, anterior cingulate cortex, and prefrontal cortex. The anterior cingulate appears particularly important for the emotional aspect. Patients with lesions here report that pain still occurs but doesn't bother them. They can detect and localize painful stimuli but lack the normal emotional response. Pain perception is highly variable and context dependent. The same injury can produce different pain intensity depending on circumstances. Soldiers injured in battle sometimes report little pain until after the battle ends. Athletes may not notice injuries during competition. The emotional state, attention, expectation, and meaning attributed to pain all influence how it's experienced. This variability reflects pain modulation by descending pathways from the brain to the spinal cord. These pathways can amplify or suppress pain signals. The periaqueductal gray in the midbrain and rostral ventromedial medulla in the brainstem project to the spinal dorsal horn and release neurotransmitters that inhibit pain transmission. This endogenous pain modulation system can be activated by stress, focused attention, or expectation of pain relief. The gate control theory of pain, proposed in the 1960 seconds, helped explain some of this modulation. The theory suggests that non-noxious sensory input can inhibit pain transmission in the spinal cord, closing the gate to pain signals. This explains why rubbing an injury reduces pain. Mechanoreceptor input activates inhibitory interneurons in the dorsal horn, reducing nociceptive transmission. While the original theory has been refined, the basic principle that pain is modulated at multiple levels, from spinal cord to cortex, remains valid. Placebo analgesia demonstrates the power of expectation and belief in pain modulation. If you believe a treatment will reduce pain, it often does, even if the treatment is inert. This isn't imaginary or faked. Brain imaging shows that placebo analgesia activates the endogenous pain modulation system, reducing activity in pain processing regions. The expectation of relief triggers real physiological changes that reduce pain perception. Chronic pain, unfortunately, represents a failure of the pain system's normal protective function. Acute pain serves the useful purpose of signaling tissue damage and promoting healing behavior. Once healing is complete, pain should resolve. But in chronic pain, pain persists long after healing, sometimes without any identifiable ongoing tissue damage. The pain system itself has become dysfunctional. Chronic pain can result from peripheral sensitization, where nociceptors become hyperexcitable after injury or inflammation. Damaged tissue releases inflammatory mediators that lower nociceptor thresholds and increase their responsiveness. This produces hyperalgesia, increased pain from normally painful stimuli, and allodynia, pain from normally innocuous stimuli like light touch. While this sensitization is adaptive acutely, increasing protection of injured tissue, if it persists, it becomes pathological. Central sensitization occurs when neurons in the spinal cord and brain become hyperexcitable after sustained nociceptive input. Synaptic changes strengthen pain pathways while weakening inhibitory control. The result is amplified pain sensitivity that persists even after peripheral input returns to normal. In severe cases, central sensitization can maintain chronic pain even in the absence of peripheral pathology. Neuropathic pain results from damage to the nervous system itself rather than from tissue damage. Nerve injury, diabetes, shingles, or neurological diseases can damage sensory neurons or central pain pathways. The result is often burning, shooting, or electric pain that doesn't respond well to conventional pain medications. Neuropathic pain reflects abnormal signal generation in damaged nerves or abnormal processing in the central nervous system. Phantom limb pain occurs in most amputees. After limb amputation, patients typically continue to feel the missing limb's presence and often experience pain in the phantom limb. This demonstrates that pain perception doesn't require peripheral input. Phantom pain likely results from maladaptive cortical reorganization after deferentation. The cortical region that formerly processed input from the now absent limb receives input from adjacent body parts, but this rearrangement creates aberrant activity that the brain interprets as pain from the missing limb. Pain serves essential protective functions when working properly. It teaches through experience. You learn not to touch hot stoves or walk barefoot on sharp gravel. It detects internal pathology, the chest pain of heart attack, the abdominal pain of appendicitis, the headache of meningitis. While medical diagnosis has gone far beyond relying solely on pain for localization, pain remains an important early warning system. But pain's protective value applies primarily to acute pain. Chronic pain that persists without serving any protective function is merely suffering. This distinction is important medically and ethically. Treating acute pain requires balancing pain relief against the information pain provides. Treating chronic pain aims for maximum relief since the pain serves no useful purpose. Temperature comfort is important for well-being beyond avoiding extremes. Humans have preferred ambient temperatures where thermal sensation is neutral and temperature regulation requires minimal effort. This thermoneutral zone varies with clothing, activity level, acclimatization, and individual differences, but generally falls around 20 to 25 degrees Celsius for lightly clothed resting adults. Outside the thermoneutral zone, discomfort increases even without reaching painful levels. Chronic exposure to uncomfortable temperatures affects mood, sleep, cognitive performance, and health. Access to temperature-controlled environments is a major determinant of quality of life, which explains the huge energy expenditure devoted globally to heating and cooling buildings. Thermal comfort during sleep is particularly important. Core body temperature drops during sleep as part of normal circadian rhythm. Optimal sleep occurs in cool environments, roughly 16 to 19 degrees Celsius, that facilitate this temperature drop. Too warm or too cold disrupts sleep architecture and reduces sleep quality. Individual differences in temperature preference and pain sensitivity are substantial. Women on average prefer slightly warmer ambient temperatures than men, possibly reflecting differences in metabolic rate and body composition. Pain thresholds and tolerance vary widely. Some variation is genetic, influenced by variants in genes encoding ion channels, neurotransmitters, and pain modulation systems. Some reflects experience. Repeated pain exposure can increase tolerance through habituation or decrease it through sensitization. Cultural attitudes toward pain also vary. Some cultures emphasize stoicism and discouraging pain expression. Others allow or encourage pain expression. These attitudes shape not just pain behavior, but pain experience itself, demonstrating again that perception is not simple sensation, but involves interpretation, meaning, and context. Temperature and pain, then, are essential components of the somatosensory system. They provide information complementary to touch. Where touch tells you what you're contacting, temperature tells you its thermal properties, and pain warns when contact threatens damage. Together, they create a comprehensive system for monitoring and protecting the body's surface, detecting everything from gentle, pleasant touch to dangerous, painful assault. The next step in understanding these senses is seeing how the brain organizes and interprets all this somatosensory information, creating conscious tactile experience and guiding appropriate responses. Sensory signals from millions of receptors in the skin must ultimately reach the brain to become conscious experience. The journey from skin to consciousness involves multiple stages of processing, organization, and interpretation. Understanding this pathway reveals not just how touch works, but how the brain transforms physical stimulation into subjective perception. Touch information travels via distinct pathways depending on what's being signaled. The dorsal column medial lemniscal pathway carries information about fine discriminative touch, vibration, and proprioception. The spinothalamic pathway carries pain and temperature information, along with crude touch. These pathways ascend separately through much of the nervous system before converging in the cortex. The dorsal column pathway begins when mechanoreceptors activate sensory neurons whose cell bodies reside in dorsal root ganglia adjacent to the spinal cord. The central processes of these neurons, effectively axons, enter the spinal cord and turn upward without synapsing, ascending in the dorsal columns. This white matter tract runs up the posterior aspect of the spinal cord, divided into the gracile fasciculus, carrying information from the legs and lower body, and the cuneate fasciculus, carrying information from the arms and upper body. These axons ascend all the way to the medulla, the lowest part of the brainstem, where they synapse in the dorsal column nuclei, the gracile nucleus medially, and cuneate nucleus laterally. Second-order neurons from these nuclei send their axons across the midline, a crossing called the decussation of the medial lemniscus, and then ascend in a tract called the medial lemniscus to the thalamus. This decussation means that the right side of the brain receives touch information from the left side of the body and vice versa. This crossed organization is preserved throughout the nervous system for most senses and for motor control, though the evolutionary reason for this crossing remains somewhat mysterious. In the thalamus, medial lemniscal axon synapse in the ventral posterior lateral nucleus, or VPL, which handles body information, and the ventral posterior medial nucleus, VPM, which handles face information carried by the trigeminal nerve. The thalamus is the sensory relay station for nearly all ascending information, not just touch, but also vision and audition. It's a critical gateway where sensory signals are filtered, modulated by descending cortical input, and prepared for cortical processing. From the thalamus, third order neurons project via the posterior limb of the internal capsule, a white matter pathway, to the primary somatosensory cortex, also called S1, located in the postcentral gyrus of the parietal lobe. This gyrus runs from roughly the top of the head down the lateral side to near the sylvian fissure just behind the central sulcus that separates parietal from frontal cortex. S1 contains four distinct regions called Brodmann areas 3A, 3B, 1, and 2, arranged in parallel strips running down the postcentral gyrus. Each receives somewhat different inputs and processes different aspects of touch. Area 3A receives primarily proprioceptive information. Area 3B receives cutaneous mechanoreceptor input and is the primary receiving area for tactile information from the skin. Area 1 processes texture information. Area 2 integrates touch with proprioception to extract information about object shape and size. All four areas are organized somatotopically, meaning they contain maps of the body surface, where adjacent body parts are represented in adjacent cortical regions. The famous sensory homunculus depicts this map, starting from the top of the postcentral gyrus and moving laterally and down. You encounter representations of toes, foot, leg, hip, trunk, neck, arm, hand, fingers, face, lips, and tongue. The map is continuous but grotesquely distorted, with huge representations of hands, especially fingertips, and lips and tongue, and tiny representations of the trunk and proximal limbs. This distortion reflects receptor density and behavioral importance rather than physical size. Your fingertips don't contain more skin area than your back, but they contain far more receptors and are far more important for tactile discrimination. The cortical magnification devotes proportionally more neural processing power to important body regions, enhancing their acuity. The organization within S1 is not just a simple map, but hierarchical. Areas 3A and 3B are primary receiving areas, getting direct input from the thalamus. They process basic features, which receptors are active, at what intensity. They project to areas 1 and 2, which extract more complex features like texture and shape. Areas 1 and 2 inches turn project to secondary somatosensory cortex, S2, located in the parietal operculum just posterior to the sylvian fissure. S2 receives convergent input from multiple S1 areas and integrates information across larger skin regions and from both sides of the body, while S1 is almost entirely contralateral, processing the opposite body side. S2 has substantial bilateral representation. Neurons here often respond to touch on either hand, suggesting a role in comparing input across body sides or in integrating touch from both hands when manipulating objects. Beyond S2, tactile information flows to posterior parietal cortex, particularly areas 5 and 7. This region integrates somatosensory input with visual and auditory information to create multimodal representations of space and objects. Neurons here encode not just where touch occurred, but where the touched body part is located in external space, requiring integration of tactile information with proprioception and visual information about limb position. Posterior parietal cortex is crucial for visually guided reaching and grasping. Damage here can produce deficits in reaching to targets despite intact vision and motor control. It's as if the patient cannot properly integrate visual information about target location with proprioceptive information about limb position to compute the appropriate movement. The pathway for pain and temperature information differs from discriminative touch. Nociceptors and thermoreceptors activate sensory neurons whose axons enter the spinal cord and immediately synapse in the dorsal horn. Second-order neurons cross the midline within a few spinal segments and ascend in the anterolateral quadrant of the spinal cord in the spinothalamic tract. This tract has multiple components. The lateral spinothalamic tract, carrying pain and temperature, projects to VPL in the thalamus and then to S1, similar to discriminative touch. But spinothalamic fibers also project to medial and intralaminar thalamic nuclei, which project diffusely to cortex, including cingulate and insular cortex. These pathways mediate the affective and arousal aspects of pain rather than precise localization. The spinoreticcular and spinomesencephalic tracts project to brainstem reticular formation and periaqueductal gray, contributing to arousal, autonomic responses, and descending pain modulation. This distributed pain network explains why pain has both sensory, discriminative components, where and how intense, and affective, motivational components, how unpleasant and urgent. Cortical processing of pain occurs in a network, often called the pain matrix, including S1, S2, insular cortex, anterior cingulate cortex, and prefrontal cortex. S1 provides localization and intensity information. Insular cortex integrates pain with interoceptive information about body state. Anterior cingulate cortex processes the unpleasantness and motivational aspects. Prefrontal cortex is involved in cognitive modulation, attention to pain, and pain-related decision-making. Neuroplasticity in somatosensory cortex is substantial. The cortical maps are not fixed, but constantly reorganized based on use and experience. If a finger is amputated, its cortical representation doesn't remain silent. Within weeks to months, neighboring representations from adjacent fingers or the palm expand to occupy the deprived territory. This reorganization can be adaptive, increasing acuity in remaining body parts, but it can also be maladaptive, contributing to phantom limb sensations and pain. Conversely, increased use of a body part expands its cortical representation. String musicians have enlarged cortical representations of their fingering hand compared to non-musicians. Blind Braille readers show enlarged representation of the reading finger. This use-dependent plasticity reflects Hebbian learning mechanisms. Neurons that are active together strengthen their connections, while inactive connections weaken. The cortical map continuously adjusts to reflect current behavioral demands. Attention powerfully modulates somatosensory processing. The same tactile stimulus produces larger responses in S1 when you attend to it than when you ignore it. This attentional modulation begins surprisingly early, even at thalamic levels, suggesting that attention doesn't just filter already processed sensory information, but modulates sensory processing itself. This has practical implications. Pain, in particular, is highly attention dependent. Distraction can substantially reduce pain perception, while focusing attention on pain amplifies it. Mindfulness approaches to chronic pain teach patients to alter their relationship with pain, partly by changing attentional patterns, observing pain without excessive focus or avoidance. Somatosensory cortex damage produces predictable deficits depending on location and extent. Lesions to S1 impair discriminative touch on the contralateral body side. Patients can detect that they've been touched, but cannot precisely localize where or discriminate two nearby points as separate. Texture and shape discrimination are impaired. Proprioception may be affected, particularly with more posterior lesions affecting areas 2 and 5. Interestingly, pure S1 lesions often preserve pain and temperature sensation, which rely more on insular and cingulate cortex. However, the affective response to pain may be altered. Patients might report detecting painful stimuli, but not finding them as bothersome, particularly with anterior cingulate damage. Posterior parietal lesions produce more complex deficits. Patients may show neglect, failing to attend to or respond to stimuli on the contralesional side, despite intact sensory detection. They may show extinction, detecting a single stimulus on either side, but failing to detect a contralesional stimulus when a simultaneous ipsilesional stimulus is present. These deficits suggest that posterior parietal cortex is crucial not just for processing sensory information, but for directing attention to it. Posterior parietal lesions produce more complex deficits. Patients may show neglect, failing to attend to or respond to stimuli on the contralesional side, despite intact sensory detection. They may show extinction, detecting a single stimulus on either side, but failing to detect a contralesional stimulus when a simultaneous ipsilesional stimulus is present. These deficits suggest that posterior parietal cortex is crucial not just for processing sensory information, but for directing attention to it. Tactile agnosia or asteriognosis is the inability to recognize objects by touch despite intact basic tactile sensation. Patients can detect that they're touching something and can describe some of its properties, smooth or rough, hard or soft, but cannot integrate these features to identify the object. This typically results from lesions to S2 or posterior parietal areas involved in integrating tactile features into object representations. Lesions affecting the posterior column pathway before it reaches the cortex produce similar deficits. Damage to the dorsal columns in the spinal cord, which can occur in tabes dorsalis, a complication of syphilis, or in vitamin B12 deficiency, eliminates discriminative touch and proprioception from body regions below the lesion. Patients develop sensory ataxia, uncoordinated movement due to lack of proprioceptive feedback. They must watch their feet to walk and cannot perform fine motor tasks without visual guidance. The somatotopic organization throughout the pathway means that small lesions produce deficits limited to specific body parts. A small stroke affecting the hand area of S1 impairs touch discrimination in the contralateral hand while sparing the rest of the body. This organization has clinical utility. The location of sensory deficits helps localize lesions. Somatosensory evoked potentials, electrical potentials recorded from the scalp following brief tactile stimuli, allow non-invasive assessment of pathway integrity. By stimulating peripheral nerves and recording cortical responses, clinicians can determine whether signals successfully traverse the pathway. Abnormal or absent responses indicate dysfunction somewhere along the route, helping diagnose conditions affecting peripheral nerves, spinal cord, or brain. Transcranial magnetic stimulation, or TMS, allows non invasive modulation of cortical activity. By delivering brief magnetic pulses through the skull, TMS can temporarily disrupt or enhance cortical processing. When applied to S1, TMS can disrupt tactile discrimination, creating temporary deficits similar to lesions. This technique helps establish causal relationships between brain regions and functions, something neuroimaging alone cannot do. Functional imaging with fMRI or PET reveals somatosensory cortex organization in living humans. When subjects are touched on different body parts, activity appears in corresponding regions of S1. These studies confirm the somatotopic organization demonstrated by earlier electrical stimulation studies in surgical patients and can track reorganization following injury or training. Tactile imagery, imagining tactile sensations without actual stimulation, activates many of the same cortical regions as real touch. This suggests that S1 and related areas are involved not just in processing external input, but in generating internal representations of touch. This makes sense for motor planning. To predict the tactile consequences of a planned movement, you need to simulate what touch will result. The somatosensory cortex also interacts extensively with motor cortex, S1, and primary motor cortex, M1, are adjacent, separated only by the central sulcus, and are densely interconnected. This anatomical proximity reflects functional relationship. Skilled movement requires constant tactile feedback, and M1 needs immediate access to sensory information to guide ongoing movements. Lesions affecting both sensoromotor cortex produce more severe motor deficits than pure motor cortex lesions because the feedback loop is disrupted. Beyond primary areas, higher order somatosensory regions in parietal cortex integrate tactile information with other senses and with memory to support object recognition, spatial awareness, and action planning. When you reach out and grasp a coffee cup, you're integrating visual information about its location and shape with tactile feedback about contact and grip forces, proprioceptive information about your arm and hand configuration, and memory about cups' typical weight and how to grasp them. This integration occurs in posterior parietal cortex and adjacent regions. The transformation from receptor activity to conscious perception is not a simple feed-forward process. Descending projections from cortex back to thalamus, brainstem, and even spinal cord modulate sensory processing at every level. These feedback connections allow cortical areas to adjust their own inputs, effectively controlling what information reaches consciousness. Attention, expectation, and behavioral context all influence this modulation. For example, when you search for something by touch in a bag, attention to tactile inputs increases, enhancing S1 responses. When you're focused on a visual task, tactile responses decrease, filtering out irrelevant touch information. This dynamic modulation allows the brain to flexibly adjust sensory processing to match current behavioral goals. Consciousness of touch seems to require cortical processing. Spinal reflexes can respond to tactile stimulation without consciousness. Pull your hand from a hot stove before you consciously register pain. But to be aware of touch, signals must reach the cortex. Exactly what cortical processing is necessary or sufficient for consciousness remains debated. Some argue that S1 activation alone produces conscious touch. Others argue that widespread activity, including prefrontal areas, is necessary. The binding problem applies to touch as in other senses. When you grasp an object, different features, texture, temperature, shape, weight are processed in different cortical areas. Yet you experience a unified object, not a collection of separate features. How the brain binds these distributed representations into unified, conscious percepts is not fully understood, but likely involves temporal synchronization of neural activity across regions representing different features. Touch illusions demonstrate that cortical processing involves inference and interpretation, not just faithful representation of inputs. The previously mentioned cutaneous rabbit and Aristotle illusion reveal that perception is constructed based on expectations and learned patterns. The rubber hand illusion provides another example. If you watch a rubber hand being stroked while feeling synchronous strokes on your hidden real hand, you begin to feel ownership of the rubber hand. Threatening the rubber hand produces anxiety and defensive responses. This illusion demonstrates that body ownership, the feeling that a body part is yours, emerges from multisensory integration and can be surprisingly malleable. Individual differences in cortical organization contribute to differences in tactile sensitivity and skill. Some variation is genetic, affecting receptor types and densities, nerve fiber properties, and cortical architecture. Some reflects experience. Extensive tactile training reorganizes cortical maps and enhances perception. Some reflects attention and cognitive factors. Some people naturally attend more to tactile information, producing better performance on tactile tasks. Blind individuals often show enhanced tactile abilities, particularly those who read Braille. Brain imaging reveals that in blind Braille readers, visual cortex is recruited for tactile processing. Areas that normally process vision are activated by touch. This cross-modal plasticity may contribute to enhanced tactile acuity. It demonstrates the brain's remarkable ability to reassign cortical areas to different functions based on input patterns. The somatosensory cortex is not an isolated island processing only touch. It's intimately connected with motor cortex, with other sensory areas, with memory systems, with attention and decision-making networks. Understanding the somatosensory cortex means understanding it as part of an integrated system where sensation, perception, cognition, and action continuously interact. From skin receptors to conscious experience involves multiple transformation stages. Physical stimulation becomes receptor potentials, then action potential patterns, then synaptic transmission and integration in successive processing stages, then distributed cortical activity, and finally somehow subjective experience. Each stage adds processing, filtering noise, enhancing relevant features, integrating with other information, comparing with predictions and memories, ultimately constructing perception that guides adaptive behavior. This system, from the molecular mechanisms of receptor transduction to the network dynamics of cortical processing, enables us to interact physically with the world, to manipulate objects with precision, to feel the comfort of warm sun on skin or the warning of sharp pain, to experience the social connection of a handshake or embrace. Touch connects us to the physical reality of our own bodies and the world we inhabit. The somatosensory cortex is where these physical contacts become conscious, meaningful experience that shapes our behavior and our sense of self. Having explored how individual sensory systems work, we now turn to the question of how they work together. We've examined vision, hearing, balance smell, taste, and touch as separate systems, but in real experience, they constantly interact, integrating information to create unified perception. This multisensory integration is our next topic, revealing how the brain combines different sensory channels into coherent experience of a unified world. We've explored each sense as if it operates independently, tracing separate pathways from specialized receptors through dedicated brain regions. This analytical approach is useful for understanding how individual sensory systems work, but it's not how you actually experience the world. Your experience is unified, multisensory, seamless. When someone speaks to you, you don't separately process the auditory information of their voice and the visual information of their face movements. You perceive a person speaking, an integrated experience where auditory and visual information combine automatically and unconsciously. This multisensory integration is not optional or effortful. It happens automatically, early in processing, and powerfully shapes perception. In many situations, multisensory information provides better perception than any single sense alone. The brain evolved not as a collection of independent sensory modules, but as an integrated system for extracting useful information about the world from all available sources. Understanding how senses collaborate reveals fundamental principles of how the brain constructs perception. The simplest form of multisensory enhancement occurs when multiple senses provide redundant information about the same event. If you see and hear someone clapping, either sense alone tells you clapping is occurring, but together they provide more reliable detection, especially in noisy or ambiguous conditions. This redundancy speeds reaction time. You respond faster to audiovisual stimuli than to purely visual or purely auditory ones, even though the stimuli arrive simultaneously. The brain appears to use a statistical decision rule, combining evidence across senses to reach faster, more confident perceptual judgments. More interesting is when different senses provide complementary information. Vision provides excellent spatial resolution, but poor temporal resolution. Audition provides excellent temporal resolution, but poor spatial information. Combining them gives you precise information about both when and where events occur. Touch tells you about surface texture and compliance. Vision tells you about color and fine spatial details. Together, they support object recognition better than either alone. The ventriloquist effect demonstrates audio-visual integration. When you watch a ventriloquist, the dummy's mouth moves while the ventriloquist speaks. Despite knowing the sound comes from the ventriloquist, you perceive it coming from the dummy. Vision captures sound localization. This makes sense in most natural situations. Visible and audible events from the same source typically occur at the same location. The brain assumes spatial coincidence and adjusts perceived sound location to match visual location. This effect is not limited to entertainment. It occurs continuously in everyday life. When you watch someone speak, you perceive their voice as coming from their mouth, even though sound localization, based purely on auditory cues, is less precise. The visual information about lip movements enhances and spatially focuses the auditory perception. The McGurk effect reveals even more dramatic audiovisual integration for speech. If you watch a video where the visual shows someone saying ga, but the audio plays ba, you often perceive an intermediate sound like da, something not present in either sensory input. The brain fuses the conflicting auditory and visual information, creating a percept that represents a compromise. This demonstrates that speech perception is inherently multisensory, integrating auditory and visual information about articulation. The temporal rule for multisensory integration states that sensory signals are bound together only if they occur close in time. The window varies by sense combination, typically 100 to 300 milliseconds. Signals occurring within this window are assumed to arise from the same event and are integrated. Signals separated by longer intervals are treated as separate events. This makes sense. Related sensory information from a single event typically arrives nearly simultaneously, while information from different events does not. The spatial rule states that signals are integrated more strongly if they occur at the same or nearby locations. Seeing a flash and hearing a beep at the same location produces stronger integration than if they're spatially separated. However, this rule is flexible. If other cues suggest a single source, even spatially separated signals can be integrated, as in the ventriloquist effect, where you know the voice and dummy should go together. The inverse effectiveness principle describes how multisensory enhancement is strongest when individual unisensory signals are weak or ambiguous. When visual and auditory signals are both clear and strong, multisensory enhancement is modest. But when one or both are degraded, near threshold or ambiguous, multisensory integration produces dramatic improvement. This makes adaptive sense. You benefit most from combining information when any single source is unreliable. Brain regions involved in multisensory integration include the superior colliculus, a midbrain structure important for orienting responses, and various cortical association areas. The superior colliculus receives visual, auditory, and somatosensory inputs and contains neurons that respond to multiple sensory modalities. These multisensory neurons show response enhancement. They fire more vigorously to combined audiovisual stimuli than to either alone. This enhanced response may support faster, more reliable orienting to behaviorally relevant events. In cortex, early sensory areas were long thought to be purely unisensory. Visual cortex processes only vision, auditory cortex only sound. But recent research reveals that even primary sensory areas receive input from other modalities. Primary auditory cortex responds weakly to visual stimuli. Primary visual cortex shows modulation by sound. These cross-modal influences are subtle compared to the primary sensory input, but can modulate processing significantly. More robust multisensory integration occurs in association cortices. The posterior parietal cortex integrates visual, auditory, and somatosensory information to create spatial representations. The superior temporal sulcus responds to both auditory and visual biological motion, like speech and body movements. The intraparietal sulcus integrates visual and proprioceptive information for visually guided reaching. These association areas combine information from multiple senses to extract features that no single sense provides well. The binding problem in multisensory integration is figuring out which signals to combine. In a crowded environment with multiple sound sources and visible events, how does the brain determine which sounds go with which sites? The brain uses various cues: temporal synchrony, spatial coincidence, past experience about what typically goes together. Usually these cues agree, and binding is unambiguous. When cues conflict, as in the McGurk effect, perception can become confused or illusory, revealing the inferential nature of binding. Cross-modal attention links attention across senses. Attending to a visual location enhances auditory processing at that location and vice versa. This spatial attention operates supramodally across sensory modalities rather than being confined within each sense. It makes sense behaviorally. If something interesting is happening at a particular location, you benefit from enhancing all sensory processing of that region, not just one modality. Similarly, attending to an object enhances processing of all its sensory features across modalities. If you're searching for your ringing phone, attending to the sound source enhances visual processing of that location, helping you spot the phone. This object based attention binds multisensory features belonging to the same object, treating the object as a unified target for attentional resources. Multisensory integration affects not just perception but action. Reaching for objects requires integrating visual information about object location with proprioceptive information about limb position. Catching a ball integrates visual motion information with predictions about ball trajectory and motor commands to move your hand to the intercept point. Playing a musical instrument requires integrating auditory feedback about produced sounds with tactile feedback from finger positions and visual information about notation. The temporal binding of perception and action involves predicting sensory consequences of movements. When you move your eyes, the visual world remains stable even though the image on your retina shifts. The brain uses a copy of the motor command, an efference copy, to predict the sensory change and subtract it from actual sensory input. What remains is motion in the external world, not just motion across your retina. This predictive integration of motor and sensory information is essential for distinguishing self-produced from externally caused sensory changes. Sensory substitution demonstrates the brain's flexibility in multisensory processing. Blind individuals can learn to navigate using tactile or auditory displays that encode visual information. A camera captures images, which are converted to tactile patterns on the skin or auditory spatial patterns. After training, users report phenomenology resembling vision. They perceive objects at a distance, not just on their skin or in their ears. Brain imaging shows visual cortex activation during use of these devices, suggesting the brain treats the remapped information as quasi-visual. This plasticity reveals that sensory cortices may be defined more by what information they process, spatial layouts, motion patterns, than by which sensory modality delivers it. Given appropriate input, cortical areas can process information from novel sources, blurring the distinction between modalities. Synesthesia represents unusual cross-sensory association, where stimulation of one sense automatically triggers perception in another. In grapheme color synesthesia, the most common form, letters or numbers trigger color perception. The letter A might always appear red, B blue, regardless of actual color. In chromesthesia, sounds trigger color perception. Some individuals experience tastes as shapes or smells as colors. These experiences are automatic, consistent over time, and genuinely perceptual, not merely associations or metaphors. Synesthesia appears to result from atypical cross-wiring between sensory regions, either excessive anatomical connections or reduced inhibition, allowing normally weak connections to produce conscious perception. Genetic factors contribute. Synesthesia runs in families. It's more common in artists and creative individuals, possibly because the cross-modal associations enhance creative thinking. Importantly, Synesthesia demonstrates that cross-modal connections exist in everyone's brain. Synesthetes simply experience more strongly what's usually below consciousness. Even non-synesthetes show cross-modal correspondences. High-pitched sounds are associated with bright colors and sharp shapes, low-pitched sounds with dark colors and round shapes. These correspondences appear automatically and influence perception and behavior even without conscious awareness. Multisensory illusions reveal integration principles. The sound-induced flash illusion occurs when a single visual flash is accompanied by two beeps. Most people perceive two flashes, even though only one occurred. The auditory information about number overrides visual information, presumably because audition has better temporal resolution and the brain trusts it for number judgments. The double flash illusion demonstrates that audition can create visual percepts. The temporal ventriloquism effect shows that vision can alter perceived timing of sounds. These illusions aren't failures, but reveal the brain's strategy. Weight each sensory channel according to its reliability for the task at hand and integrate to produce the best estimate. Bayesian integration models describe mathematically how the brain might optimally combine multisensory information. Each sensory estimate has uncertainty. Vision might estimate object location with some variability. Proprioception provides another estimate with different variability. The optimal strategy is to weight each estimate by its reliability. Precise estimates get more weight, uncertain estimates less. The combined estimate is more precise than either alone. Behavioral and neural data suggest the brain performs something like this optimal integration. Development of multisensory integration is protracted. Infants show some multisensory abilities early. Newborns orient towards sounds, integrating auditory localization with motor control. But more sophisticated integration develops gradually through childhood. The temporal and spatial windows for integration are initially broad and narrow. With experience, neural circuits for multisensory integration mature slowly, with protracted development continuing into adolescence. Experience shapes multisensory integration. Growing up in typical environments with correlated audiovisual events, speech for instance, trains the system to bind these appropriately. Abnormal experience, like early sensory deprivation, can impair multisensory integration. This has clinical implications for conditions affecting sensory input early in development. Autism spectrum disorders often involve atypical multisensory integration. Some individuals with autism show reduced multisensory enhancement or abnormal temporal windows for integration. This may contribute to difficulties with speech perception and social interaction, which heavily rely on integrating auditory and visual cues. Understanding multisensory processing in autism might suggest interventions to improve integration and enhance functional outcomes. Schizophrenia is associated with abnormal multisensory integration and increased susceptibility to multisensory illusions. This may relate to broader difficulties in binding sensory information into coherent percepts and in distinguishing self-generated from externally generated sensations. The hallucinations characteristic of schizophrenia might reflect failures of predictive integration between motor commands and sensory consequences. Aging affects multisensory integration. Older adults show broader temporal windows and sometimes stronger multisensory enhancement, possibly compensating for declining unisensory abilities. Multisensory cues can improve balance, speech perception, and memory in older adults, suggesting that emphasizing multisensory information might help maintain function during aging. Multisensory integration, then, is not an optional addition to unisensory processing, but a fundamental principle of how the brain works. The senses did not evolve independently, but as a coordinated system, they provide overlapping, complementary information about the same world, and the brain evolved to exploit this redundancy. Integration happens automatically, early, and powerfully shapes perception. Understanding this reveals that asking which sense is most important misses the point. What matters is how senses work together, combining strengths, compensating for weaknesses, creating perception that's richer and more reliable than any single sense could provide. This integrated sensory system doesn't spring into existence fully formed. It develops systematically from before birth through adulthood, shaped by genetic programs and environmental experience. How this development unfolds and how sensory experience during development shapes the mature sensory system is what we'll explore next. The sensory systems you possess as an adult developed over years, beginning long before birth and continuing through childhood into adolescence. This development involves both genetic programs that unfold on predetermined schedules and experience dependent refinement where sensory input shapes neural circuits. Understanding sensory development reveals not just how you came to perceive as you do, but illuminates fundamental principles about brain plasticity and the role of experience in shaping neural function. The senses develop in a specific sequence, reflecting both their structural complexity and their functional importance at different developmental stages. Touch develops first, hearing and vestibular sense next, then taste and smell, with vision developing last and undergoing the most prolonged postnatal refinement. Touch sensation begins remarkably early. By 8 weeks of gestation, the fetus responds to touch around the mouth. This makes functional sense. The rooting reflex, turning toward touch on the cheek, is essential for feeding immediately after birth. By 14 weeks, tactile sensitivity has spread across the face, palms, and soles. By 20 weeks, the entire body surface is touch sensitive. This early development reflects the relative simplicity of mechanoreceptors compared to the specialized structures required for other senses. The fetus experiences substantial tactile stimulation in utero. Contact with the uterine wall, amniotic fluid currents, self-touch as the fetus explores its own body and the umbilical cord. This early tactile experience likely contributes to body schema development, the brain's representation of body structure and boundaries. Premature infants who lose this contained tactile environment sometimes show developmental differences that gentle touch and containment can partially address. The vestibular system develops prenatally and is functional by mid-gestation. The semicircular canals and otolithic organs form early and respond to head movements and maternal movement that rocks the fetus. This early vestibular experience may be essential for normal development of motor coordination and spatial processing. The rhythmic rocking and acceleration experienced in utero may explain why infants find rocking soothing. It replicates familiar vestibular stimulation. Hearing develops during the second half of pregnancy. The cochlea reaches adult size and structure by about 20 weeks gestation, though it continues to mature. By 25 to 26 weeks, fetuses respond to loud sounds, showing heart rate changes and movement. By the third trimester, the auditory system is functional, and the fetus can hear sounds from the environment, filtered and muffled by the mother's body. The prenatal auditory environment is surprisingly rich. The mother's heartbeat, about 60 to 80 beats per minute, provides constant rhythmic stimulation. Digestive sounds, blood flow, the mother's voice, and muffled external sounds all reach the fetus. Lower frequencies penetrate better than high frequencies, so bass sounds and prosody, the rhythm and intonation of speech, come through more clearly than high frequency consonants and fine details. Newborns show clear recognition of sounds experienced prenatally. They prefer their mother's voice to unfamiliar voices, a preference that emerges from prenatal auditory experience. They prefer stories their mother read aloud during late pregnancy to novel stories. They prefer their native language to foreign languages, responding to the characteristic prosodic patterns they heard in utero. This demonstrates that auditory learning begins before birth and that prenatal auditory experience shapes postnatal preferences. Taste and olfaction are functional late in gestation. Taste buds form by 8 to 12 weeks, and by late pregnancy, the fetus swallows amniotic fluid, exposing taste receptors to chemical stimuli. The composition of amniotic fluid is influenced by maternal diet, so the fetus experiences taste related to what the mother eats. This early taste experience appears to shape later preferences. Infants whose mothers consumed anise, garlic, or other strongly flavored foods during pregnancy show preferences for those flavors after birth. The olfactory system is functional before birth, responding to odorous molecules in amniotic fluid. Newborns can discriminate odors and show preferences for familiar smells, including the smell of their own amniotic fluid, which suggests they learned these preferences prenatally. They quickly learn to recognize their mother's scent, showing preferential orientation toward her scent within days of birth. This olfactory recognition supports bonding and feeding. Vision develops latest and requires the most postnatal refinement. The eye structures form during pregnancy, but visual experience is obviously limited in the dark environment of the uterus. Some light penetrates through the abdominal and uterine walls, and late-term fetuses may detect bright lights shined on the mother's abdomen, but vision plays no functional role before birth. At birth, the visual system is anatomically present but immature. Visual acuity is poor, about 20/400, roughly 40 times worse than normal adult acuity. Newborns can detect light and large high-contrast patterns, but cannot resolve fine details. The retina is functional but immature, particularly the fovea, which continues developing for months. The optic nerve is incompletely myelinated, slowing signal transmission. Visual cortex is present, but massively disorganized compared to adult structure. Newborn visual preferences reveal what their limited system can process. They prefer to look at high-contrast patterns over uniform fields, at patterns with more elements over simple patterns, at curved over straight contours. Remarkably, they show preferential looking at face-like patterns, stimuli with roughly face configuration, two dark regions above a light region, even though they cannot resolve facial details. This face preference may be innate, present from birth, or may develop within hours from postnatal visual experience. Visual development proceeds rapidly after birth, but requires years to complete. Acuity improves steadily, reaching near adult levels by about age 3 to 5, though subtle improvements continue through middle childhood. Color vision develops over the first few months as cone photoreceptors mature and cortical circuits for color processing refine. Depth perception emerges around 3 to 4 months as binocular disparity mechanisms become functional, assuming both eyes develop normally and remain aligned. The visual cortex undergoes dramatic postnatal development. At birth, neurons in visual cortex respond to visual stimulation but are broadly tuned and disorganized. With visual experience, neurons become selective for specific orientations, directions of motion, and disparities. Cortical organization sharpens, with neurons with similar preferences clustering into columns. Connections that support feature detection and integration strengthen, while inappropriate connections are pruned away. This refinement requires visual experience during a critical period, roughly the first several years of life, when neural plasticity is highest. Deprivation of normal visual input during this critical period produces permanent impairment. This was demonstrated dramatically in classic studies of kittens raised with vision restricted to vertical stripes. When later exposed to normal vision, they lacked neurons responding to horizontal orientations and showed impaired perception of horizontal contours. In humans, conditions that disrupt early visual experience, strabismus, where the eyes are misaligned, or unilateral cataracts, can produce amblyopia, reduced visual acuity that cannot be corrected with glasses. The eye itself is healthy, but the cortical processing is permanently impaired due to abnormal experience during the critical period. Early treatment, realigning the eyes or removing cataracts before age 2 to 3, can prevent amblyopia, but delayed treatment often fails because the critical period has closed. Critical periods occur for all sensory systems, though timing and duration vary. Auditory critical periods for speech sound discrimination close relatively early, by around 10 to 12 months. This explains why native language phonetic categories are readily acquired in infancy, but foreign language distinctions become difficult to learn later. Children exposed to two languages from birth acquire both easily, but learning a second language after early childhood is more difficult and typically results in accented pronunciation. Cochlear implants for congenital deafness work best when provided early, ideally before age 2 or 3. Delay beyond the critical period results in poorer speech outcomes, as auditory cortex has already been partially reassigned to other functions or has developed abnormally without auditory input. Sensory experience shapes brain development through multiple mechanisms. Hebbian plasticity, neurons that fire together wire together, strengthens connections between neurons that are consistently co-activated. Connections that aren't used are weakened or eliminated. This experience, dependent plasticity, refines initially imprecise circuits into precise ones tuned for the experienced environment. Neurotrophic factors released by active neurons support their survival and growth. Inactive neurons receive less support and may die or lose connections. This competitive process means that neurons processing frequently encountered stimuli expand their cortical representation at the expense of neurons processing rare stimuli. The result is that your sensory systems become specialized for your environment. If you grow up in a carpentered environment full of straight lines and right angles, your visual system becomes especially tuned to these features. If you grow up in a forest environment with curved, irregular forms, your tuning differs. If you grow up hearing tonal languages like Mandarin, where pitch conveys meaning, your auditory system develops enhanced pitch processing compared to speakers of non-tonal languages. This plasticity is both blessing and curse. It allows optimal adaptation to experienced environments, but creates vulnerability if early experience is atypical. Children growing up with chronic ear infections causing fluctuating hearing loss can develop subtle auditory processing difficulties even after hearing is restored. Children raised in impoverished sensory environments show delays in sensory and cognitive development that enrichment can partially, but not always fully remediate. Binocular vision development illustrates the importance of appropriate experience. For stereopsis to develop, both eyes must provide clear, aligned images during the critical period. If one eye is misaligned or has degraded optics, the brain cannot properly integrate the two eyes' inputs. Rather than perceiving double vision, which would be disabling, the brain suppresses input from the deviant eye. If uncorrected, this suppression becomes permanent, producing amblyopia and loss of stereoscopic depth perception. Treatment involves correcting the optical problem with glasses, patching the good eye to force use of the amblyopic eye, or surgery to realign the eyes. These treatments work if provided early, but become less effective as the critical period closes. This demonstrates that normal sensory development requires not just anatomically intact sense organs, but appropriate patterns of sensory experience. Cross-modal plasticity occurs when one sense is impaired. Blind individuals show enhanced auditory and tactile abilities compared to sighted individuals. Brain imaging reveals that visual cortex in blind individuals is activated by auditory and tactile tasks, effectively repurposed for other senses. This plasticity is most pronounced for early onset blindness, occurring within the critical period, demonstrating that sensory cortices can be flexibly assigned based on input patterns. However, this cross-modal plasticity may complicate vision restoration. If a congenitally blind individual gains sight late in life through cataract removal or corneal transplant, visual cortex has been repurposed. The restored visual input must compete with established auditory and tactile functions. Such individuals often struggle with vision, finding it confusing and overwhelming, and some prefer to continue using their enhanced non-visual senses rather than learn to see. Language development depends critically on early sensory experience. Children acquire language through exposure without explicit instruction during a sensitive period in early childhood. Auditory experience hearing speech or visual experience seeing sign language during this period allows language to develop naturally. Deprivation of linguistic input during this period, as in tragically rare cases of severe neglect or isolation, produces permanent language impairment that cannot be fully remediated later. This demonstrates that the brain is prepared to acquire language with dedicated neural machinery for language processing, but requires experience during a critical developmental window to realize this potential. Language acquisition isn't purely learning, as it requires too little explicit instruction and shows too uniform developmental milestones across diverse environments. Nor is it purely innate, as it requires appropriate experience. It represents an interaction between biological preparation and environmental input. Perceptual narrowing occurs in multiple sensory domains during the first year. Newborn infants can discriminate phonetic contrasts from any language, including distinctions not present in their native language. By 10 to 12 months, they've specialized, maintaining ability to discriminate native language contrasts, but losing sensitivity to non-native contrasts. Similarly, young infants discriminate faces from any ethnic group, but become better at discriminating faces from familiar ethnic backgrounds and worse at others by the end of the first year. This specialization represents adaptive plasticity. The brain focuses on processing stimuli most common in the environment, becoming expert at those while losing flexibility for uncommon stimuli. For a child growing up in a monolingual community, Losing sensitivity to foreign phonetic contrasts has little cost and allows more efficient processing of native speech sounds. For a child in a multilingual environment, broader phonetic sensitivity is maintained. Multisensory integration develops gradually. While infants show some basic multisensory abilities, sophisticated integration of temporal and spatial cues continues developing through childhood. The temporal window for audiovisual integration is broad in infants and narrows with experience as the brain learns the typical delays between different sensory signals from the same source. Spatial rules for integration similarly refine with experience exploring how sensory signals correspond across modalities. Motor development and sensory development are intimately linked. Reaching for objects requires integrating visual information about object location with proprioceptive information about arm position. The ability to reach accurately emerges around 4 to 5 months, coinciding with maturation of both visual spatial processing and sensory motor coordination. Walking requires integrating vestibular, proprioceptive, and visual information for balance, emerging around 12 months as these systems mature and coordinate. Active exploration is crucial for sensory development. Infants don't passively receive sensory input, but actively seek it, looking, listening, touching, tasting, smelling. This active exploration allows learning about sensoromotor contingencies, how movements produce sensory changes. When you move your hand, the visual image moves predictably. When you vocalize, you hear your own voice. These contingencies, learned through experience, are foundational for distinguishing self from other and for understanding causation. The importance of active experience was demonstrated in classic studies where kittens were raised in darkness except for brief periods in a lighted environment. Some kittens could move freely, others were passively transported in gondolas, receiving similar visual input but without active control. The actively exploring kittens developed normal vision. The passive kittens showed visual deficits, demonstrating that active sensory motor experience is more effective for development than passive exposure. Sensitive periods vary across sensory systems and aspects of processing. For basic sensory detection, critical periods are relatively early and short. For more complex perceptual abilities and for multisensory integration, sensitive periods extend later into childhood. For some aspects of sensory processing, subtle plasticity continues throughout life, though early experience is disproportionately influential. Individual differences in sensory development result from both genetic variation and environmental differences. Some infants are constitutionally more sensitive to sensory stimulation, showing stronger responses to sights, sounds, and touch. This temperamental variation, partly heritable, predicts aspects of personality and behavior. Highly sensitive infants may be more reactive to stress, but also more responsive to positive experiences. Premature birth affects sensory development. Premature infants develop in the NICU environment, which differs dramatically from the uterus, brighter, louder, with more handling and procedures. This atypical early sensory experience may contribute to developmental differences sometimes seen in preterm infants. Efforts to provide more womb-like environments with reduced light and noise, contained positioning, and kangaroo care promoting skin-to-skin contact aim to support more typical sensory development. Sensory processing disorder, where individuals have difficulty processing and responding to sensory information, may reflect atypical sensory development. Some children are over-responsive, finding ordinary stimulation overwhelming. Others are under-responsive, seeking intense stimulation. Still others show sensory seeking or avoiding behaviors. While sensory processing issues are common in autism spectrum disorder, they can occur independently. Understanding sensory development has practical implications. It suggests that enriching sensory environments supports development, though overstimulation can be counterproductive, particularly for young or sensitive infants. It explains why early intervention for sensory impairments is crucial, capitalizing on critical period plasticity. It reveals that apparently innate abilities like face recognition or language may depend on early experience that's so universal we don't notice its role. Adolescent brain development includes continued sensory system refinement. While basic sensory functions mature in childhood, higher level perceptual and multisensory integration continues developing. Myelination of long-range connections proceeds through adolescence, improving signal transmission speed and timing. Synaptic pruning refines cortical circuits, eliminating unused connections and strengthening used ones. These changes may support improved selective attention, working memory for sensory information, and sensory motor integration underlying complex skills. The development of sensory expertise in domains like music or sports involves extensive practice during periods of heightened plasticity. Musicians who begin training in childhood show different brain organization than those who start later, with enlarged representations of relevant body parts and enhanced auditory processing. While adults retain capacity for learning, early experience more profoundly shapes brain structure and function. Aging brings gradual sensory decline across all modalities. Visual acuity decreases, particularly for near vision due to presbyopia. Hearing loss, especially for high frequencies, becomes common, affecting speech perception in noisy environments. Olfactory and gustatory sensitivity decrease, affecting appetite and flavor enjoyment. Tactile sensitivity decreases, particularly vibration sense. Balance function declines, increasing fall risk. These age-related changes result from multiple factors: receptor loss, degradation of sensory structures like the lens becoming cloudy or cochlear hair cells dying, slowed neural transmission, changes in central processing. While some sensory decline is inevitable, maintaining sensory stimulation, treating treatable conditions like cataracts, and using assistive devices like hearing aids can preserve function and quality of life. Importantly, the brain retains plasticity throughout life, though it decreases with age. Continued sensory engagement, learning new skills, and enriched environments support continued sensory and cognitive function in aging. The developing sensory systems of infancy eventually become the aging sensory systems of late life, completing the developmental arc. Sensory development, then, is not a simple unfolding of genetic programs, but an intricate dance between biology and experience. Genes provide the initial architecture and the capacity for plastic change. Experience refines this architecture, shaping circuits to match the specific environment encountered. The result is sensory systems exquisitely tuned to extract information from the world they developed in, systems that enable successful navigation and interaction with the environment from infancy through old age. This developmental perspective reveals both the robustness and fragility of sensory systems. Robust in that typical development occurs reliably across diverse environments with only minimal necessary inputs. Fragile in that specific early experiences during critical periods are essential, and their absence produces permanent impairment. Understanding this balance informs interventions for sensory impairments, educational practices, and appreciation of how early experiences shape the sensory world we inhabit. Having traced sensory development from fetal life through maturity, we now turn to what happens when this development goes awry or when mature sensory systems fail. Sensory disorders, their causes, consequences, and the brain's remarkable capacity for adaptation and compensation reveal both the importance of normal sensory function and the resilience of the nervous system when challenged. These are the topics we explore next. The complexity of sensory systems means there are countless ways they can malfunction. Receptors can be damaged, sensory structures can degrade, neural pathways can be interrupted, processing regions can be lesioned. Yet, despite this vulnerability, sensory impairments often reveal the remarkable plasticity and adaptability of the nervous system. When one sense fails, others often compensate. When function is partially lost, the remaining capacity reorganizes to maximize utility. Understanding sensory disorders illuminates not just what can go wrong, but how the brain adapts to maintain function in the face of deficit. Vision disorders are among the most common and thoroughly studied. Refractive errors, where the eye's optics don't properly focus light on the retina, affect the majority of adults. Myopia, or nearsightedness, occurs when the eyeball is too long or the cornea too curved, causing distant objects to focus in front of the retina. Hyperopia, or farsightedness, results from the opposite problem. The eyeball is too short or the cornea too flat, causing near objects to focus behind the retina. Astigmatism involves uneven curvature of the cornea or lens, producing different focal lengths in different planes and blurred vision at all distances. All three are easily corrected with glasses or contact lenses that adjust the refraction to restore sharp focus. Laser surgery can reshape the cornea, permanently correcting refractive errors in many cases. Despite their prevalence, refractive errors don't impair the visual system itself, just the eye's optics. Once focus is corrected, vision is normal. Presbyopia, the age-related loss of accommodation, affects everyone who lives long enough. The lens gradually hardens with age, losing its ability to change shape and focus on near objects. By the mid-40s, most people need reading glasses. Presbyopia progresses until around age 60, when the lens has lost essentially all accommodation. This is normal aging, not pathology, though it's certainly inconvenient. Cataracts, clouding of the lens, develop in most people who live into their 80 seconds. The normally transparent lens proteins clump together, scattering light and reducing the amount reaching the retina. Vision becomes dim, blurry, and washed out. Colors appear less vibrant. Glare becomes problematic, especially from headlights at night. Cataracts develop gradually, so people often don't realize how impaired their vision has become until after surgical correction restores clarity. Cataract surgery, one of the most common and successful surgical procedures, involves removing the clouded natural lens and replacing it with an artificial intraocular lens. The procedure is usually quick, done under local anesthesia, and recovery is rapid. Vision improvement can be dramatic, restoring not just acuity, but color perception and contrast sensitivity. Glaucoma involves damage to the optic nerve, often associated with elevated intraocular pressure. Fluid called aqueous humor is continuously produced inside the eye and must drain through channels at the angle where iris meets cornea. If drainage is impaired, pressure builds, compressing the optic nerve and gradually killing retinal ganglion cells whose axons form the nerve. The damage begins in the peripheral visual field and progresses slowly. Congenitally blind individuals who gain sight late in life, through surgery correcting conditions that caused blindness, often struggle profoundly with vision. Despite normal eye function after correction, they have difficulty recognizing objects visually, distinguishing figures from backgrounds, and using vision for navigation. Years of blindness during critical developmental periods mean visual cortex was repurposed for other functions and cannot easily revert to processing vision. Many such individuals continue relying primarily on their established non-visual strategies despite having functional vision available. Hearing impairments range from mild difficulty hearing quiet sounds or understanding speech in noise to profound deafness. Conductive hearing loss results from problems in the outer or middle ear, preventing sound from reaching the cochlea, earwax blockage, perforated eardrum, fluid in the middle ear from infection, or otosclerosis, where abnormal bone growth immobilizes the stapes. Conductive losses typically affect all frequencies similarly and can often be treated medically or surgically. Sensorineural hearing loss results from cochlear or auditory nerve damage. The most common cause is damage to outer hair cells from aging, noise exposure, certain medications, or infections. Unlike conductive loss, sensorineural loss is typically frequency specific, usually affecting high frequencies first. This is why people with age-related hearing loss, presbycusis, complain they can hear people talking but cannot understand what they're saying. They're missing the high-frequency consonant sounds that carry much of speech intelligibility. Sensorineural hearing loss is usually permanent, as mammalian hair cells don't regenerate. Hearing aids amplify sound, particularly at affected frequencies, which helps but cannot restore normal hearing. Modern hearing aids are sophisticated, using digital processing to reduce background noise, enhance speech, and adjust output for individual hearing loss patterns. Cochlear implants can restore hearing for profound sensorineural hearing loss when hair cells are extensively damaged, but the auditory nerve remains functional. An electrode array inserted into the cochlea directly stimulates nerve fibers with electrical signals generated by an external processor. While the sound quality differs from natural hearing, with limited frequency resolution and altered timbre, many implant users develop excellent speech comprehension. Music perception remains challenging as pitch and timbre are poorly reproduced. Early cochlear implantation in congenitally deaf children produces better outcomes than delayed implantation, reflecting auditory critical periods. Children implanted before age 2 to 3 typically develop near normal speech and language. Delayed implantation results in more variable outcomes as auditory cortex has developed abnormally or been recruited for other functions. Tinnitus, perceiving sound in the absence of external sound, affects about 15% of adults. It's typically described as ringing, buzzing, hissing, or whistling, and can range from minor annoyance to severe impairment of quality of life. Tinnitus often accompanies hearing loss and appears to result from altered activity in auditory cortex, possibly compensation for reduced input from the damaged cochlea. No cure currently exists, though sound therapy, cognitive behavioral therapy, and hearing aids can help manage it. Deafness, particularly if congenital or early onset, affects language and cognitive development if not addressed. However, sign languages provide complete linguistic access. Deaf children acquiring sign language from birth develop language normally, showing typical developmental milestones just through a visual rather than auditory modality. Brain regions that process spoken language in hearing individuals process sign language in deaf signers, demonstrating that language capacity is independent of sensory modality. Vestibular disorders produce vertigo, dizziness, and balance problems. Benign paroxysmal positional vertigo, BPPV, is common and occurs when calcium carbonate crystals dislodge from the otolithic organs and migrate into semicircular canals. Head position changes cause these crystals to move, inappropriately stimulating the canal and creating false signals of rotation. The result is intense spinning sensation, often with nausea, triggered by specific head positions like rolling over in bed. Repositioning maneuvers can move the crystals out of the canal, resolving symptoms. Meniere's disease involves episodes of severe vertigo lasting hours, accompanied by fluctuating hearing loss, tinnitus, and ear fullness. It's thought to result from abnormal endolymph fluid dynamics, but mechanisms are incompletely understood. Treatment includes diet changes, medications, and sometimes surgery. Between episodes, function may be normal or show progressive hearing loss. Parosmia, distorted smell perception, can occur after olfactory nerve damage. Smells are perceived but incorrectly. Roses might smell like gasoline, coffee like sewage. This likely reflects disordered regeneration with olfactory neurons connecting inappropriately. Parosmia can be even more distressing than anosmia, as familiar pleasant smells become unpleasant. Taste disorders are less common than smell disorders, partly because the taste system is more robust with redundant innervation from multiple cranial nerves. Ageusia, complete taste loss, is rare. Hypogeusia, reduced taste sensitivity, occurs with aging, some medications, and conditions affecting the tongue. Dysgeusia, distorted taste, can result from medications, dental problems, or neurological conditions. Because most taste loss actually reflects smell loss, differentiating requires careful testing. True taste disorders specifically affect the 5 basic tastes: sweet, salty, sour, bitter, umami. Much more commonly, smell loss eliminates flavor, which patients describe as taste loss, even though their gustatory system functions normally. Tactile impairments result from peripheral neuropathy affecting sensory nerves or from central lesions affecting somatosensory pathways or cortex. Diabetic neuropathy, the most common peripheral neuropathy, damages small nerve fibers, producing numbness, tingling, or pain in a glove and stocking distribution affecting hands and feet. This sensory loss increases injury risk, as minor cuts or pressure sores go unnoticed and can become severely infected. Central somatosensory impairments from stroke, trauma, or other brain lesions produce numbness and loss of tactile discrimination on the contralateral body side. Fine motor control is impaired even if motor cortex and pathways are intact, because tactile feedback is essential for skilled movement. Rehabilitation focuses on compensating strategies and on promoting recovery through intensive sensory and motor practice. Chronic pain represents a pathological sensory state where pain persists without serving protective function. Neuropathic pain from nerve damage produces burning, shooting, or electric sensations. Fibromyalgia involves widespread pain and tenderness, possibly reflecting central sensitization. Complex regional pain syndrome produces severe pain, often disproportionate to the initial injury, with associated changes in skin color, temperature, and sweating. Chronic pain is challenging to treat, often requiring multimodal approaches, including medications, physical therapy, psychological interventions, and sometimes nerve blocks, or spinal cord stimulation. Understanding pain as involving both sensory and emotional components has led to treatments targeting the affective dimension, like cognitive behavioral therapy, which can reduce suffering even when pain sensation persists. Syndromes where multiple senses are affected include Usher syndrome, combining congenital deafness with progressive vision loss from retinitis pigmentosa. This dual sensory loss is particularly challenging as individuals typically adapt to deafness using vision, which then itself fails. Early intervention, teaching tactile communication methods like tactile sign language, becomes essential. Across all sensory impairments, the brain's plasticity allows remarkable adaptation. Remaining sensory modalities enhance sensitivity. Cortical representations reorganize, expanding processing capacity for preserved functions. Cognitive strategies develop to compensate for lost sensory information. Social support and assistive technology further enable adaptation. Yet sensory impairments also reveal the limits of compensation. No amount of plasticity can fully replace vision for reading visual text or hearing for perceiving speech and noise. Quality of life is impacted, and many individuals with sensory impairments experience depression and social isolation. This underscores the importance of prevention where possible, early treatment, and development of better assistive technologies and rehabilitation strategies. Understanding sensory disorders also reveals what sensory systems normally do. We tend to take our senses for granted until they fail. Only then do we fully appreciate how much information they provide, how seamlessly they work, how central they are to daily function and quality of life. The sensory systems don't just inform us about the world, they fundamentally shape our experience of being in the world, our capacity to interact with it, our emotional life, our social connections, our sense of self. When they fail, these aspects of existence are all affected, revealing how profoundly our senses make us who we are. We've explored the five senses systematically, their receptors and structures, their neural pathways, their cortical processing, their development, their disorders. But this analytical approach, useful as it is for understanding mechanisms, risks missing something essential. Your senses are not merely information-gathering systems. They are fundamentally constitutive of your conscious experience, your sense of self, your relationship to the world. Understanding the senses in their full significance requires stepping back from mechanism to consider meaning, what it means to be a sensory creature, how perception shapes consciousness and identity, why the sensory world you inhabit is deeply personal even while connecting you to shared reality. Start with a fundamental observation. Consciousness is embodied. You don't experience yourself as a disembodied mind, but as an embodied being located in space, interacting with a physical world through a physical body. This embodiment is given to you through your senses. Proprioception and the vestibular sense tell you where your body is and how it's oriented. Touch defines your boundary, the surface where you end and the world begins. Vision, hearing, smell, taste all connect you to the external environment, providing information about what's out there beyond your skin. Without sensory input, embodied consciousness dissolves. Sensory deprivation experiments, where subjects float in darkness and silence with minimal tactile stimulation, produce profound alterations in consciousness within hours. Hallucinations, time distortion, disorientation, loss of sense of self. The brain, deprived of sensory anchoring, generates its own input, producing experiences untethered from reality. This demonstrates that normal consciousness is not generated purely internally, but emerges from continuous sensory engagement with the environment. Your body schema, the brain's representation of your body's structure and capabilities, is fundamentally sensory. It's built from proprioceptive information about limb positions, tactile information about body surface and boundaries, vestibular information about orientation, and visual information when you observe your own body. This schema is what allows you to reach out and touch your nose with your eyes closed, to walk without consciously thinking about where your feet are, to grasp objects with appropriate grip force. It's continuously updated by sensory input and guides motor planning. The flexibility of the body schema is revealed by tool use. When you use a tool skillfully, it becomes incorporated into your body schema. A tennis racket becomes an extension of your arm. A blind person's cane becomes an extension of their tactile sense. They feel objects at the cane's tip, not in their hand. This incorporation involves sensory remapping. Mechanoreceptors responding to vibrations transmitted through the tool, proprioceptors monitoring the tool's position, brain areas representing the body extending to include the tool. The boundary between self and world is fluid, defined by use rather than biology. The rubber hand illusion demonstrates body schema flexibility experimentally. Watching a rubber hand being stroked while feeling synchronous strokes on your hidden real hand produces feeling of ownership of the rubber hand. The visual and tactile inputs are consistent with the rubber hand being yours, and the brain accepts this interpretation, updating the body schema accordingly. This shows that body ownership, the feeling that this body is mine, emerges from multisensory integration and can be manipulated. Phantom limbs after amputation further reveal the body schema's independence from actual body structure. Most amputees continue feeling their missing limb's presence, can move it voluntarily, feel it positioned in space. This phantom limb reflects the persistent body schema representation even after sensory input has ceased. The cortical representation of the limb doesn't disappear when the limb is amputated, but remains active, generating sensations attributed to the now absent limb. Sensory experience shapes not just body representation, but personality and preferences. Individual differences in sensory sensitivity contribute to temperamental variation. Some individuals are constitutionally more sensitive to sensory stimulation, showing lower thresholds and stronger responses. This sensory processing sensitivity affects how people interact with their environment, how much stimulation they prefer or find overwhelming, which activities they enjoy or avoid, how they respond to stress. Highly sensitive individuals often prefer quiet, calm environments, avoid crowds and loud events, notice subtleties others miss, process information deeply before acting. Less sensitive individuals may seek stimulation, enjoy intense sensory experiences, feel bored in quiet settings. These differences, partly heritable and evident from infancy, shape life choices, where you live, what job you choose, what hobbies you pursue, whom you befriend. Sensory sensitivity is one dimension of personality, influencing how you relate to the world. Food preferences, shaped largely by taste and smell, become part of identity. Cuisine is culturally specific, and your food preferences connect you to your cultural heritage. The flavors you grew up with taste like home, like family, like belonging. Food memories are often emotionally charged. Grandmother's cooking, holiday meals, first dates. These associations, linking flavors to emotions and memories, through the direct connections between olfactory cortex and limbic system make food preferences deeply personal. The same applies to other sensory preferences. Some people are highly sensitive to visual aesthetics, drawn to beautiful environments, distressed by ugliness. Others are musically inclined, with rich emotional responses to music. Some are tactilely oriented, valuing texture and physical comfort. These sensory inclinations shape what brings you pleasure, what you seek out, what you create if you're artistically inclined. Sensory memory is peculiarly powerful for the chemical senses. A smell can instantly evoke a memory with remarkable vividness, transporting you mentally to another time and place. This Proust phenomenon reflects the direct projection from olfactory cortex to hippocampus and amygdala, bypassing the thalamus. Smells access memory and emotion in ways other senses don't, producing nostalgia, comfort, or distress depending on associations. Your personal history of sensory experiences shapes your sensory world. Places you've lived, people you've known, experiences you've had, all leave sensory traces. The smell of pine trees recalls childhood vacations. A particular song brings back a relationship. The feel of sand evokes beach trips. These sensory memories are not merely facts stored in memory, but recollections that reactivate sensory cortices, producing attenuated versions of the original perceptual experience. Remembering is partly re experiencing. Culture shapes sensory attention and interpretation. Different cultures emphasize different senses. Western cultures tend to privilege vision, evident in language. We say, I see, meaning I understand. We value insight and vision. Other cultures emphasize other senses. Some emphasize sound and music. Some emphasize smell or taste. These cultural emphases affect not just what people attend to, but how they think, using sensory metaphors grounded in their emphasized modalities. Cultural practices shape sensory experience directly. Cuisines differ dramatically across cultures, producing different flavor experiences and preferences. Aesthetic traditions differ. What's beautiful or harmonious in one culture may not be in another. Even basic perceptual habits vary. People from Western carpentered environments show greater susceptibility to geometric illusions than people from less carpentered environments, reflecting learned visual processing strategies. Sensory substitution and augmentation technologies are beginning to extend sensory capabilities. Cochlear implants provide hearing to the deaf. Retinal implants may eventually restore vision to the blind. Sensory substitution devices convert visual information to tactile or auditory patterns, allowing blind individuals to perceive spatial information through other modalities. These technologies not only restore function, but raise philosophical questions about the nature of perception. If you learn to see through your skin, is that really vision? It suggests that sensory modalities are defined more by what information they convey than by which receptors provide it. Technologies that augment normal senses could extend human perception beyond its evolved limits. Devices detecting infrared or ultraviolet radiation, magnetic fields, ultrasound, or other stimuli imperceptible to unaided senses could expand the perceptual world. Early experiments with such devices suggest that with practice, novel sensory inputs can become intuitive, integrated into normal perception. This plasticity hints at human potential for radically expanded sensory experience. Altered sensory experience produces altered consciousness. Psychedelic drugs produce visual hallucinations. Synesthesia, altered time perception. Sensory deprivation produces hallucinations and disorientation. Meditation practices that focus on sensory experience can produce altered states where perception becomes more vivid or where the boundary between perceiver and perceived seems to dissolve. These alterations reveal that normal consciousness is one configuration of sensory processing among many possible ones. Mindfulness practices teach paying attention to sensory experience in the present moment. The feeling of breath moving in and out, the sensations of the body, sounds occurring now. This deliberate attention to sensation has effects beyond momentary awareness. It can reduce stress, improve emotional regulation, enhance well being. The mechanism may involve shifting from conceptual, abstract processing to direct sensory experience, from thinking about to sensing. The distinction between sensing and perceiving matters here. Sensing is the immediate contact with sensory information, light, sound, pressure, chemical. Perceiving is the interpretation, recognizing objects, extracting meaning, relating to memory and knowledge. Normally, perception dominates. You don't see light patterns, you see objects. You don't hear air pressure variations, you hear speech or music. But you can shift attention to raw sensation, perceiving light and dark, loud and soft, rough and smooth, without immediately categorizing or interpreting. This capacity to attend to sensation itself reveals that perception is constructed, that there's a gap between sensory input and perceptual experience where processing occurs. Normally, this gap is invisible, perception immediate and automatic. Attending to sensation makes the gap apparent, revealing perception as active interpretation rather than passive reception. Sensory experience grounds you in the present moment in ways abstract thought cannot. When you're thinking about the past or future, planning or remembering, you're not fully present. Sensory experience is always now, always here. This is why sensory grounding techniques help with anxiety. Focusing on what you can see, hear, touch, smell, taste right now interrupts anxious rumination and returns attention to immediate reality. Your sensory world is unique yet shared. The wavelengths of light, the air pressure variations of sound, the molecules triggering smell and taste, the mechanical forces producing touch. These are objective, measurable physical phenomena, but your subjective experience of them, what it's like for you to see red, or hear middle C, or smell coffee, is private, inaccessible to others. We assume similarity, that your red resembles my red, but we can never be certain. Individual differences in sensory processing mean that your perceptual world differs somewhat from everyone else's. If you're a super taster, flavors are more intense for you. If you're colorblind, you don't distinguish colors others readily see. If you have hyperacusis, sounds are painfully loud at levels others find comfortable. These differences create genuinely different sensory worlds, different qualia, the subjective qualities of experience. Yet despite this subjectivity, sensory experience connects us to shared reality. We navigate the same physical world, even if we perceive it slightly differently. We communicate about sensory experiences, developing shared vocabularies and understandings. The physical properties we sense, while subjectively experienced, correspond to real features of the environment. Your senses connect you both to external reality and to other people through shared reference to that reality. Sensory deprivation reveals the importance of sensory connection. Solitary confinement, eliminating social and sensory stimulation, is psychologically devastating. Prisoners in solitary report hallucinations, anxiety, depression, loss of sense of time, and self. Sensory connection to the environment and through it to other people is essential for psychological well being. We are not self contained minds, but beings whose consciousness emerges from sensory engagement with world and others. Sensory deprivation reveals the importance of sensory connection. Solitary confinement, eliminating social and sensory stimulation, is psychologically devastating. Prisoners in solitary report hallucinations, anxiety, depression, loss of sense of time and self. Sensory connection to the environment and through it to other people is essential for psychological well being. We are not self contained minds, but beings whose consciousness emerges from sensory engagement with world and others. The sensory richness available in the world is effectively infinite. You could spend a lifetime exploring the visual intricacy of a forest, the auditory complexity of a symphony, the textural variety of fabrics, the flavor nuances of wines, the fragrances of flowers. Sensory experience offers inexhaustible depth, yet modern life often involves sensory deprivation or monotony. Windowless offices, repetitive soundscapes, processed foods with simplified flavors. Attending to sensory richness, seeking diverse sensory experiences, engaging deeply with sensory details can enhance quality of life. Artists specialize in attending to and creating sensory experiences. Painters see color relationships and light effects others miss. Musicians hear harmonic and rhythmic complexities that untrained listeners experience vaguely. Chefs perceive flavor combinations and textural contrasts that make food memorable. This expertise reflects both talent and extensive practice, directing attention to sensory dimensions, developing discriminative ability, and learning to create experiences that engage and move others. Anyone can cultivate sensory awareness, paying attention to what you see, really looking rather than glancing, listening carefully to sounds, noticing their qualities, attending to tactile sensations, textures, and temperatures, savoring flavors and aromas rather than eating mindlessly. This deliberate sensory engagement enriches experience, making ordinary moments more vivid and meaningful. The relationship between sensory experience and emotion is intimate. Certain sensory experiences produce emotional responses. Soft textures, comfort, harsh sounds agitate, sweet tastes please, foul smells disgust. These sensory emotion linkages are partly innate, reflecting evolutionary adaptive responses, but are also learned through experience. Sensory experiences associated with positive events become pleasant. Those associated with negative events become aversive. This sensory conditioning means that your emotional life is partially structured by sensory associations. Particular places, smells, sounds, textures can trigger emotions by activating memories of events in which they occurred. This can be therapeutic, as in using comforting sensory experiences to regulate emotions, or problematic, as in trauma triggers where sensory reminders produce distressing emotional responses. The development of self-awareness involves sensory experience. Infants must learn to distinguish self from other, to recognize that some sensory experiences are caused by their own actions, while others are externally generated. This is learned through sensoromotor contingencies. When I move my hand, I see it move and feel proprioceptive feedback. When someone else moves, I see motion without corresponding proprioceptive signals. These contingencies teach the boundary between self and world. Mirror neurons, which fire both when performing an action and when observing someone else perform it, blur this boundary in interesting ways. They create a neural resonance with others' actions, potentially supporting empathy and social understanding by allowing you to internally simulate others' experiences. Sensory experience of others' actions activates your own sensoromotor systems, creating a bridge between self and other. Synesthesia, where sensory experiences automatically trigger perceptions in other modalities, reveals unusual cross-wiring in sensory systems. For synesthetes, these cross-modal experiences are genuine perceptions, not just associations. A synesthete, seeing colors when hearing music, isn't imagining the colors or associating them metaphorically. They're perceiving them with conscious visual experience triggered by auditory input. This demonstrates that the sensory modalities, while anatomically separated, can become linked through neural connections. It suggests that the distinction between modalities is somewhat arbitrary, a product of how peripheral receptors and processing streams happen to be organized rather than a fundamental feature of perception itself. In principle, any sensory quality could trigger any other given appropriate neural connections. The cultural history of sensory experience is part of human history. Different historical periods and cultures have valued and cultivated different sensory experiences. Medieval Europe emphasized smell in religious contexts with incense and perfumes. The Enlightenment privileged vision and rational observation. Romanticism valued emotional responses to natural beauty perceived through all senses. Modern consumer culture stimulates visual and auditory senses through advertising and entertainment while often neglecting others. Technology is changing sensory experience in unprecedented ways. Virtual reality creates immersive visual and auditory experiences of non-existent environments. Screens mediate increasing amounts of visual experience, replacing direct perception of the physical world. Recorded music allows auditory experiences divorced from live performance. Processed foods create flavors that don't exist in nature. These technological mediations offer new experiences, but also risks. Sensory monotony, reduced engagement with direct physical reality, overstimulation in some modalities, and understimulation in others. The question of what's lost and gained in technologically mediated sensory experience is important. Virtual experiences can be rich and engaging, but they lack the full sensory richness of physical reality, the smells, the tactile sensations, the peripheral awareness of context. They're also obviously representations, lacking the ontological weight of real presence. Whether this matters depends on purposes and values. For some purposes, mediated experience suffices or excels. For others, direct sensory engagement with physical reality remains essential. Sensory experience connects you to place. The sensory character of a location, its sights, sounds, smells, even its tactile qualities and climate, contributes to sense of place. People feel attachment to places partly through sensory familiarity, the particular light, the ambient soundscape, the local smells. Moving to a new place involves sensory adaptation, becoming accustomed to new sensory environments. Homesickness is partly sensory, missing familiar sensory experiences. The concept of sensory landscapes captures this. Each environment has characteristic sensory properties. Forests have particular visual patterns, sound qualities from rustling leaves and bird calls, smells of earth and vegetation, tactile sensations of humidity and temperature. Cities have different sensory signatures, visual complexity and artificial lighting, noise from traffic and crowds, smells of exhaust and food, hard surfaces, and reflected heat. These sensory landscapes shape experience of inhabiting different environments. Environmental degradation often involves sensory degradation, polluted air and water, noise pollution, visual blight. Conversely, environmental quality involves sensory richness and pleasantness, clean air, natural soundscapes, visual beauty, access to varied textures and temperatures. Human well being depends not just on functional environments, but on sensorially rich, pleasant ones. As this exploration of the five senses draws to a close, return to where we began. Right now, in this moment, your senses are operating continuously. Light is striking your retinas, converting into neural signals that your brain interprets as visual experience. Sound waves are vibrating your eardrums, triggering cascades of transduction that become auditory perception. Perhaps you're aware of the pressure of your body against a surface, the temperature of the air, the position of your limbs. Perhaps there are smells or tastes in awareness. More likely, these sensations are present but in the background, not consciously attended, but nonetheless contributing to your sense of being here, now, in this place. This continuous sensory contact with the world is so constant, so automatic, that it's easy to take it for granted. The senses seem transparent, as if you directly perceive reality rather than constructing perception from sensory signals. But as we've explored throughout these chapters, perception is not simple or direct. It involves specialized receptors detecting specific forms of energy or chemical information, transduction mechanisms converting physical stimulation into neural signals, processing through multiple stages, extracting and integrating information, and finally cortical processing that somehow produces conscious experience. At every stage, perception is active, constructed, interpreted. The brain uses sensory input, but also prior knowledge, expectations, context, and goals to construct perceptual experience that's useful for guiding behavior. What you perceive is the brain's best inference about what's out there, not a direct readout of sensory data. This makes perception simultaneously reliable, usually accurately reflecting external reality, and fallible, subject to illusions when sensory input is ambiguous or when the brain's assumptions are violated. Your sensory systems connect you to the world, to your own body, to other people. They provide the information that grounds you in reality, that enables interaction and communication, that makes possible all the activities of life, from the mundane to the extraordinary. Without them, consciousness itself would be profoundly different if it existed at all. You are, in a very real sense, your sensory experience, your identity, your sense of self, your awareness of existing as an embodied being in a physical world, all emerge from and depend upon sensory input. The five senses, traditional categories though they are, capture something essential about human nature. We are visual creatures, building detailed representations of spatial layouts and objects. We are auditory creatures, communicating through sound and responding emotionally to music. We are olfactory and gustatory creatures, using chemical senses to evaluate food and connect to memory. We are tactile creatures, interacting physically with the world and each other through touch. And we are proprioceptive and vestibular creatures, maintaining our sense of embodiment and orientation in space. These senses don't operate independently, but form an integrated system, a system that's been refined through millions of years of evolution, that develops systematically through childhood, that retains remarkable plasticity throughout life, that can adapt when challenged by injury or deprivation, and that continuously constructs the rich, meaningful, subjective experience of being conscious, of being alive, of being connected through sensation to everything that exists beyond the boundary of your skin. As you continue through your day, through your life, your senses will continue their work, mostly beneath awareness, but always present, always connecting you to the world. Perhaps now, having explored how they work, you might occasionally pause to appreciate them, to notice what you're seeing, hearing, touching, tasting, smelling, to marvel at the complexity of the systems that make these experiences possible, to recognize that the sensory world you inhabit, personal and subjective as it is, nonetheless connects you to the same physical reality that every other sensory creature inhabits, creating a shared world we can navigate together despite our individual differences in how we perceive it. The five senses are your interface with reality, your window onto existence, your means of gathering the information that consciousness is constructed from. They are, quite simply, how you know the world, how the world knows you, and how you come to know yourself as a being embedded in and connected to the vast, intricate, endlessly fascinating physical universe that surrounds you through your senses. Physics becomes experience, chemistry becomes meaning, and mechanism becomes consciousness. They are the bridge between matter and mind, the foundation upon which all of human experience ultimately rests. And so, as this journey through the architecture of sensation concludes, the sensory symphony continues, moment by moment, breath by breath, as it has since before you were born and will until your final moment. Your senses connect you to the world, silently, ceaselessly, making possible everything you experience, everything you are, everything you will ever know. In the end, perhaps this is what we mean when we speak of being alive: to sense, to perceive, to experience, to be connected through our five senses to the world that contains us, sustains us, and gives meaning to our existence.